Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 432. Count non-decreasing subarrays after K operations. Yeah, that's it. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. So yeah, I think I struggle a lot with this one. Obviously I didn't solve it during the contest. Also, just to give you a heads up, I explored this problem like really deeply. Mostly for reasons that I'll talk about. But this video is like 4 or 5 hours long. 4 or 5 hours of that is live. So feel free to kind of watch the beginning, and then if you are really interested in someone who is actually grinding on one problem and try to understand why, then watch the live portion. Maybe watch it, like skip ahead as you can. But yeah. And before I do that, I want to start with what's unique to this channel, right? Which is my experience and why I struggled on this problem, and my thought process throughout, right? In a more summary way that isn't 5 hours, because I was still trying to solve it afterwards and upsolving, and I upsolved it like 3 or 4 different ways. And I'll go over all of them in kind of, maybe not in super high detail, but just kind of conceptually, right? And how I got it to it that way. But before I do that, before I recap the problem, which you can, if you could skip ahead and find my explanation, if that's what you care about, is that the reason why I didn't solve this, I think, is because I read this the wrong way. And not to say that I misread it, I just read it the wrong way. I think one thing that for this problem for me is that very early on in my contest, or like during the contest when I opened this problem, I thought that this problem was going to be symmetric. And what do I mean by that? Symmetric means that for me anyway, I mean, it could mean different things in different contexts, of course, but for me, for this problem, symmetric means that if I do going from the left to the right is the same as going from right to left. So I mistakenly assumed that it is symmetric. And the processing of the numbers. And when that happens, and maybe technically speaking, there are definitely equivalent ways, but it's just way easier in one direction. I don't know if that's even true, honestly. I think the problem is just asymmetric, meaning that, like I said, going from left to right and right to left is really different. Like I said, maybe there's some shared principles and stuff that maybe you could do it, but yeah. And the reason why this led to me not solving it is, one is obvious, because I thought to go from left to right versus right to left, which a lot of people did, I think, or at least a couple of solutions that I scanned. And the problem is that by the time I realized it was asymmetric, and I was revisiting it, thinking, I was like, oh wait, it is not symmetric, meaning that actually it is a different problem if you go backwards. Of course, if you go backwards, non-decreasing means something, you have to adjust some properties. But my problem is that I was not able to fully reset during the contest, or honestly even after the contest, when I was like, oh, it's not symmetric and I should look at it that way. And the reason is because, a lot of these problems, I talk about properties and invariants and all these things that comes up in the course of analyzing and try to figure out how to solve a problem. For me, the thing is that when I was finally able to kind of look the other way and do it backwards, there were ideas that I was playing with that was just no longer true. Or maybe, well, that is true, but also even in the other direction, right? Meaning that things that I thought was not true is actually true in the reverse direction. So that's basically kind of the idea, and I think that's why I struggled a lot with this one, is because I wasn't able to fully reset for a long time, because I spent maybe like at least 40 minutes analyzing it going left to right. And then a lot of the things were no longer true going from right to left, but I was maybe either lazy or just tired or both, and I just didn't follow it through with all the observations, and as a result, I didn't explore certain things because I just thought it wouldn't work, because I explored it in the other direction, right, or the other way around. I thought things would work, and then I'm like, oh no, it doesn't work, right? Anyway, so that's basically the it's a long premise, but I just want to, I want to kind of go over why that is the case. And if you watch the first, I don't know, hour of the live portion, you'll see that as well, is that I was really struggling. And even when I made the observation that it is asymmetric and I should consider looking at it backwards, I wasn't able to make the transition for a long time until way after the contest. Anyway, so okay, so the first thing first, problem explanation or problem solution explanation, and we'll do the progression. I actually end up solving this 4 different ways. Well, not 4 different ways, but 4 ways building off each other, right? And I would also start with the disclaimer that this is all 4 ways were after the contest. I did not get the solution. Like I didn't cheat and just copy and paste, but I was able to get a hint about the possibilities, right? And I think that's part of sometimes why it's hard, is that once you know something is possible, then you look for it and then you find it, right? But if you didn't think it's possible, you just sometimes it's easy to get stuck in local minimas or maximas where you're like, okay, I'm doing optimizations to make things work instead of doing the smarter thing and coming up with something more clever that makes it work in a better way. All right. Okay, so that's all the setting up I'm going to do. Let's actually go over the problem, right? The problem. And the first thing, as I said many times, is that this thing is asymmetric, right? So, yeah, going from right to left, what does that mean? And I'm drawing it out right now. Right? Going from right to left, what does it mean? Well, instead of non-decreasing, now, let's say, I think this is the first case, except for I'm doing it backwards. Except for now, okay, so now let's say we're going from left to right, right? Here, of course, the problem is a little bit different. Here, we care about it going down versus going up, or going down is better than going up, right? So what does that mean? Well, let's just go from left to right, right? And before I start, this is a contribution problem, right? Meaning that n is pretty big, so n squared is too slow. So that means that you have to iterate through the loop, apparently either from left to right or right to left. In this case, it's right to left, but we reverse the array, right? And then figure out the contribution of each number to the final answer in sublinear time per element to make it less than n squared, right? Anyway, so what is the naive, one way that I would think about is that, okay, so going from left to right, I wouldn't even consider the naive solution, but it's just the first thing I thought about, is that, okay, for 4, you have the second 4, it doesn't change, right? It's fine. And then now you have a 2, as we're processing the 2. Well, what does the 2 mean? Well, the 2 is fine because 2 is smaller than 4, and we don't care because in reverse is it increasing, or so yeah, we don't care, right? So here we go 1, also don't care, so that means that we get full benefit. And then now we have a 3, right? Well, what does this 3 mean? There are ways to do this, but and we'll talk about how to do it in a sec. But the idea here is that here for this 3, we care about the 4, right? Because here, or maybe we don't even necessarily care about the 4 directly, but we care about consuming the 1 and the 2, right? Because if you think about it in the other direction, then this is going to be decreasing, obviously, from 3 to 1 and 1 to and 3 to 2. So then we have to make this to 3 and this also to 3. And here we can just, well, yeah, we can just do the math, right? And what do I mean by that? That means that here, if we push everything on a stack, we would have 4, 4, we have 2, 1, 3, and this just becomes caring about the previous bigger number, which I'm not going to go over it in too deeply because this video is already going to be like 5 hours long, right? So I'm not going to go over mono queue, but this is a mono stack problem, right? And monotonic stack. Again, not gonna go over it. My apologies. You have to come back after you understand monostack. But the idea here is to get the next or the previous number that is bigger, right? And in this case, this is 4 for 3. And as a result, we just consume, right? So 3, we get rid of the 1. But what does this mean? This means that we want to plus 2 to make it a 3, right? And then now we add this, we get plus 1 to make it a 3, right? So now you can think about it as 3s, but in data structure, you could compress this together, right, to 3, right? And then now next you have a 6, right? Well, 6, what happens? Well, you have these new 3s. Let me actually write out in a different color. You have these new 3s and you have a 6, keeping in mind that they're all kind of compressed together. So then the 6 will consume these 3s by adding 3 to each one, right? And the stack allows us to kind of get the range in a quick way, though, to get actually, no, I lied. And then this is, we consume these by consuming the 3, right? But then here, we also consume the plus 2 for the 4s, right? So we consume, and then at the end, the stack will only have 6, right? So, yeah. So the first thing is that even if you have a magical thing that lets you do these updates, you have to do them faster than, you have to do each element. Like you can't do a for loop going from right to left to consume all of these. You have to look at each one at most once, right? And the reason why is because once we do an add on this number, then we never go back to it. Because now this number is encompassed in another range, right? Because for example, this 1 is now part of the 3, this 2 is part of the 3, this 4 is by itself, but after the 6, then now the 2, 1, and the 3, which is the new group of 3s, will get merged to the 6. And here we get this merged to the 6 and this merged to the 6 once, right? So, okay. These are just general principles about monostack. I know I'm going a little bit fast, but like I said, this is like a 5-hour video. So I am going a little bit fast because, well, we just have to go fast. In any case, so then now you see that these becomes range queries, right? So then now we're doing, okay, let me erase real quick some stuff. Because then now, if you think about it in terms of update queries, this 3, we update this one to plus 2, this one to plus 1, and then we end here, right? And then now this 6, we want to say, okay, well, here plus 3, and then plus 2, right? And of course, every time we do these queries, these gets merged into one, right? Because then now in the future, now we have a super interval of 6, right? This is the 6, and so forth. So then now, but what that means is that there are only at most n unique queries, right? Or all of n unique queries as a merging, right? Because every time you pop off something, you get a merge, and this is way basic monostack things, right? And I say that because I hope that if you don't understand it, please review monostack and amortization of all these things, right? Because each thing. So then now the property that we want is maybe log n for update, or right? Because we can't do an all of n update for each one, but we could do all of log n for each query. And if we're able to do that, then we're able to get this part of at least the updates, right? Okay, so this is where I'm a little bit sad, but this is where segment tree comes in, right? So segment tree, and this is very high machinery. I'm going over it really quickly because it is not necessary for this problem. But I just want to kind of show you that, like what I have done so far is very naive, right? Very straightforward. For some definition of straightforward, I don't mean to trivialize it. It's very hard. I didn't get it, right? But I just want to say, like, these are the easy parts of the harder problem. But as a result, yeah, as a result, you can use segment tree as a black box, and it just has these properties, right? And one of the versions of segment tree is that it allows you to do range update in O of log n, amortized, and also range query, range sum query in this case, in O of log n time. And why is that important? Well, okay, so let's say we process this entire thing, right? Or maybe in the middle of processing it. Well, what does that mean? Well, okay, let's go back, right? So I just went over the processing step, but we have to figure out the contribution as we go, right? Well, as we go, what does that mean? Let's clean this up a little bit. As we go, what does this mean, right? So that means that we have 4, 4, 2, 1, 3, 6. I'm remembering like it's a lottery number, but yeah. So then now, well, so the cost here is 0. The cost here is 0. The total cost is 0. This is 0, right? Well, what happens to 3? Because now there is cost. You eat up 2 of these, right? So then now this cost is going to be so we have a plus 2 here, plus 1 here, right? So then now the query becomes, okay, we're given a certain k. To satisfy this, then it just becomes a binary search query. There are other things that we're going to talk about, but at the first thing, it's going to be, you can do a binary search. Again, I'm not going to go over the binary search too deeply because this is a long video, but the idea here is that, and we'll go over the code part of this, right? So the idea here is that, okay, well, we start with the number 3 here, right? So then now we go, okay, well, if we sum up these numbers, how many k do we have, right? How many operations does it take? Here it takes 3. So if it's less than k, then we can try more number. Or if it's less than k, we try fewer numbers. And and this is just binary search stuff, right? So this goes to either here or here. And then if this is good, then maybe you extend. Maybe you extend. But if you want to think about the midpoint that you're searching, then this is the midpoint. Oops. This is the midpoint, right? So your binary search segment is like this range. This is your midpoint, and then now this range, right, is for well, okay, let's just say this is not it. So then now we search for this. We search for this range. So this is the middle, and then if it goes the other way, then we search for this range. So this is the middle, but this is the function that that corresponds to this middle in the binary search, and then now we search for here, and so forth. I'm doing the visualization really quickly, but this is binary search stuff. Implementation, we'll go with implementation now, but I just want to show you the visualization, because I think once you have the visualization, the idea is not that bad, not that it's good. But I would also say that for now, we need an optimization, because this actually time limit's exceeded, even though it's n log square n, because, well, actually let me go back real quick. The reason why this is log square n and not just log n is because this binary search is obviously log n, right? But each request, each query is also log n. So you have log n times log n, right? Okay. So this is that solution for segment tree. Again, I have this segment tree template. It's it's from a long time ago. I think I copied. I think a long time ago I asked ChatGPT, and then I kind of mixed it up, made some updates or something. But this is again very high machinery. There is lazy propagation. I'm not going to go over segment tree. We're just going to use it as a black box. It's not interesting, and it doesn't solve this problem anyway. It's a time limited situation. Anyway, so yeah. So then now I forgot one part. That's why I'm pausing. Sorry, friends. Oh wait, no. No, I didn't. This is the more complicated one. I think I'm showing you the wrong code. That's why. Sorry, hang on. Hang on a second. Yeah, I think it's this one maybe. Nope. As you can see, I spent a long time on this one. Yeah, okay. This is the one that I wanted to go over. No edit code one. Okay, whatever. Yeah, so again, I'm not going to go over segment tree, but this is the idea, right? So this is the contribution. This is a sliding window. Oh, no, sorry. It's not sliding window. Even though I have this here for some reason. So that's why it's a little bit awkward. But yeah, so now for each element, we binary search to the left, right? X is left. We do the stack thing that we talked about. This is the mono stack. So each item on the stack will contain, I wish I could edit this, but each item on the stack will contain the left index of that segment, the right index of that segment, and the X, the biggest X that was on that segment. And then as a result, well, we add to that range the delta, right? This is the delta. We add the range, and then we just we update the leftmost. And why we update the leftmost is because we pop, and then we push them as a new merged interval, right? So this is how I implement the merged interval on the stack, and it just consists of three things, which is the X value, the left and the right, and this is the delta for each item, right? So we update range in the segment tree terms, allow us to update each item by adding this number. So then now, in theory, well, segment tree will actually contain all the deltas, but now you can say that all numbers in that range is the same number, right? And then now we have a get function afterwards to get the total of things that we count. And here, also pretty straightforward-ish. Assuming that you're familiar with binary search, this is what we talked about in the visualization, right? So this is the binary search for how far to extend, and this is the query from the segment tree from the middle to the border to see if it's less than or equal to k, and this is the sum of all the addition operations, right? So this code, and this is log n, this is log n, so this is O of log square n, and this is going to be O of n, so this is going to be n log square n, which is too slow. But what I notice is a couple of things, right? What I notice is that, and this is a little bit crappy, honestly, because on Leetcode's thing, you can almost never tell whether one optimization is enough. I'll go over how I optimized it, because it's needed for the second optimization. But this first optimization was able to get accepted, but honestly, I don't know. If it didn't get accepted, I don't know. It would not have surprised me, right? But yeah, so the idea here now is that we have this segment tree solution is too slow. How do I write it without segment tree, right? With the same complexity. Well, the idea here is that, okay, when we consume, all we have to do is update or keep track of a prefix sum, right? So keeping in mind that, let's go back to this drawing real quickly. So the idea behind the prefix sum is just that, yeah, and I say it like it's easy, but honestly, it is not that easy, right? But the idea here is that, okay, well, you have all these queries, right? You have all these things. It's just that when you process this number, we now want to store prefix sum. So let's say we're making this query. What does this mean? Well, prefix sum just means that you want to get all of these number minus all of this number, right? And for this query, it is all of this number minus all of this number. So regular prefix sum stuff so far in idea, in concept. Not gonna go over prefix sum in this video. We already have been going over too much stuff, right? And I kind of keep repeating myself about how long this video is. But yeah, so we want to be able to do these, right? So how can we do these? So the idea behind prefix sum is just keeping track, honestly, of a lot of things, right? We call it that, let's go back a second, right? We have all these stacks. Let me change the color real quick. We have all these stack. We have 4, 4, 2. Let's say 2, 1, and then we go to the 3, right? And the stack so far is going to be 4, 4, 2, 1. But so that's the stack with the numbers. But you can also keep a track in second stack, and of course, it's not just the numbers, because as we said, if we have a 3, then this consumes these. So this actually has the range as well. But you can also keep track of the prefix sum up to that number, right? So that means that here we can say this is 0, 0. This doesn't do anything, so 0, this is 0. And then when you have a 3, then now we can say the prefix sum is 3, right? So we actually pop these two numbers, So we have 3 because and we also store the range, but it consists of all the numbers that we care about, right? Which is the range and the prefix sum. And the reason why we have this is that now we have, let's say we have the next number is, I don't know, a 2, right? Then now here the prefix sum is going to be a 3 because this adds 0, right? But you know, and maybe. Yeah. And then maybe you have another number which is maybe 2 is a terrible number to example, but maybe you have another number that is okay. Let's remove the 2 for a second, and also I ran out of space. Let's erase these, right? So let's say the next number is 1, then this doesn't change. But then let's say this is 2, right? Well, the 2 we yeet the 1. And adds a cost of 1, so this is 4, right? So then now you can kind of see it from left to right. The prefix sum, you have 0, 0, 3, 4, ... And then if you look at this prefix sum, it is going to be monotonically increasing because that's just how prefix sum works. But as a result, there are 2 things, right? That means that now you can binary search on a prefix sum array. Of course, now this adds a little bit of complication to it, right? Because I deleted the visualization. Oh well, sorry friends. But the idea here is that So then now let me redraw some parts of it, but not really actually. But yeah, let's say we want this is the. Let's say this is the entire range, and we want to figure out this number, right? This, just this sum, right? This range, we want to make this correct. Well, how do we do it? Well, keep in mind that we have a stack that represents range of intervals, right? So maybe you have range, so this is the stack, and then next to each other, I'm just drawing it like this, right? So maybe you have someone like this, you have someone like this. Let me actually redraw this one a little bit, right? So something like this that represents the current interval. So now when you do a query, it would basically cut it off, right? Choose a different color real quick. And really though, and now prefix sum just becomes this thing, right? Prefix sum just includes all these numbers, which we know because we calculated it here, minus, or depending on how you want to do it. So there are a couple of ways you can do it, but it's all the same, right? Which is that you take this entire range minus this number, so then it gets, so then now we have this piece, but then now we want to add this piece, and this piece is, we can figure it out because we know the numbers, right? Because we know how wide this is and the x, so then we can just figure out, what the numbers is. And that's basically the idea behind the binary search optimization without the segment tree. So okay, so let's look at that real quick. Is it this one? No. Okay, so it's this one. And the idea, I'll take out some, let me take out some print statements. And it's not trivial the way that I wrote it, but you can see that I kind of just replaced these things, right? The idea is still mostly the same, which is that, okay, we have a stack, but on this is the same stack as we saw before, but we just wanted to keep track of a prefix array. And the prefix array just includes the index and, actually this lies because I think I updated. But yeah, I mean, I made it so that it's binary searchable, right? So then here I have to write So this is the right interval and the left interval. So so prefix actually is the right interval, right index, left index, the current prefix sum, and then just so prefix sum, and then the number x. I think I lied on this one because this still uses update range. I think Oh no. I think this one was an intermediate one where I still used the segment tree to validate my answer, because basically what I did was that I assert that st dot query range from left index to all index is equal to maybe not here. Forget what this should equal to, but maybe here, right? So then we just want to update. I think this. I think this was just an intermediate one, so that I can. So okay, I think this is the one where I cheated, honestly. And by cheated, I just mean that. So this is actually a good principle to talk about a little bit, which is that I was doing this because I had a solution that I knew was right, but it was timing out. So I was just making small adjustments to it to optimize it. And I knew that I want to get rid of the segment tree. So basically we follow basic testing principles, which is that we migrate one step at a time. And here, I knew that I can get this very quickly with a prefix sum, but I just wanted to kind of keep track of this. And this is basically what we said, right? I mean, this is more expensive, but it is right in that this is just the entire range. So then we put everything in prefix, because the reason why this looks wonky is because I wanted to focus on the binary search portion, right? And the binary search, let's just say for now, and we'll update the code in a second, let's say prefix sum contains this stuff, but correctly without us doing it, right? So then now, instead of having this segment tree query, oh yeah, okay, I see. Because this is basically me making the update only to the query and not the update portion. So yeah, so I updated the query from here to here, and the query function is just, well, we binary search on prefix on the index, right? So this is where the right index comes, y is first, because then now, if you binary search bisect left on the right index, then the current index is the one that you're partially in, right? So then now I do the prefix sum, right? The total contains the total from the index that we're currently processing, meaning the right side of, it's not really a window because I don't use it, but basically it is, yeah. The total that goes up to right, so you could see me do, this is the current, this is the total up to there. So I pass it in so that we can do the math that way, which is that, yeah. Oh, I needed the second prefix sum that I didn't go over. But okay, so let's go over the binary search first, and then the binary search allow us to, yeah, the binary search allows us to find the segment that we care about. Total minus t, this is basically, like I said, the prefix, right? This is the prefix. And then the second part, it's going to be basically this part, which is part of one chunk, right? So how do we calculate the part of one chunk? I didn't go over it that quickly, but basically the idea here to calculate one chunk is that one pencil is that okay, so what is the width, right? You know the width. The width is just the number of indexes, right? So that part is trivial. And then the height, it's going to be just the x that we updated to, right? So then x is the number that we updated to inside that interval. So these are, we can say every number here is x, right? So then what does that mean? That means that all the numbers that are inside, so basically, if you think about it as a or a rectangle, so let's say you have, I don't know, I'm making up numbers, but you have 1, 2, 3, and you wanted to get and you want to say that they all go up to 4. Now you converted them all to 4s, right? Then how do you get the sum of this, right? The sum of this in an O of 1. Well, the idea here is that, okay, well, 1 plus 2 plus 3 is equal to 6, but then 4 times 3, or maybe you could say 4 plus 4 plus 4 is equal to 12. So that means that in order to make all 3 numbers to 4, it's just 12 minus 6 is equal to 6, right? So 12 minus 6 is equal to 6. So that's how you basically get the idea, right? So then here, when we do a binary search, we know what the x should be, which is the number that we changed that segment to, and then a second prefix sum. Just to be clear, this is a second prefix sum. That is the sum of the elements, because okay, the blue prefix sum is the first prefix sum, and this is the sum of the segments, right? Of the changes that we made to the segments. And then another prefix sum is to calculate, it's a regular prefix sum on the input that allow us to get the original numbers. So these are the original numbers. These are the numbers that they're on, the new numbers. And as a result, you have 12 minus 6 minus 12 minus 6 is equal to 6, right? And yeah, and there's a visualization to this, which I like, right, in general, which is that, okay, let's say we have an XY axis, you have length 1, you have length 2, you have length 3, and it doesn't have to be in incremental order. You could actually, like, it could be in any order, right? And all we know is that we want to make them 4, right? Let's say we want to make them 4, and these are some numbers, right? So then the idea here is that, well, we calculate the visualization, which makes the math a little bit easier to understand, is that we calculate the size of this rectangle, which is obviously the height is 4, the width is just the number of indexes, right? And then with the prefix sum, because we're trying to get the sum of all these deltas, right? Well, all these deltas now in visualization, let me choose a different color, is just the sum. So these numbers is just the sum of all the blue numbers, which you can get with prefix sum, which is why we do the prefix sum, minus the red rectangle is 12, minus the blue prefix sum will give us the green delta numbers. That's basically when you see this formula, that's basically what happens, right? Anyway, so that's basically what I'm trying to do here, right? We do a binary. So there are 2 prefix sums, which is why this is confusing. Or well, is one of the reasons why it's confusing. Because then you have total minus t. So this is the first prefix sum. Prefix sum on the intervals, right? And this is prefix sum on the input numbers within the same interval. So you can see that p right is just, within the same interval. Well, we're going from right to left, so then the number of this is just the width. So you just have to figure out with the target, which is the number we're binary searching on. X is the height, so this is the height thing that we talked about, and then this is the prefix sum that is what we talked about with the thing. So then this subtraction will give us the sum of the deltas, right? I know I'm going a little bit fast, but we're half an hour in and we still haven't even gotten to the next solution yet, right? So my apologies. Or more than half an hour, because I think I skipped ahead. Whatever. We're very long in. Anyway, okay. So this is how you do the query. So we submit this. There's still times out, but it's okay. We have to do this part, right? And for this part, like we haven't changed. Oh, actually, this is another optimization that I did. So I'm missing one of them. This is how I spend 4 hours, is me analyzing all these things, right? Yeah, I think this one is the one. Yeah. Okay, yeah. Okay. Let me just paste in here so I could remove some of these things. Okay, so the query code we went over, right? So now we have to do the processing. So this is the query code, exactly the same, right? I guess this is wrong because of what we talked about, but you know, you need to revisit the, just rewind. And actually, I guess we don't need the segment tree here, but yeah. Anyway, yeah. So then now we're just trying to do the math a little bit better. And actually, I think I cleaned this part up. Maybe I do have a cleaner version real quick. I think it's this one maybe. Yeah, okay. So I do have a slightly cleaner one. So let's do this. Okay. Yeah, so the query we already talked about. It is what we talked about, right? Oh wait, no. This is the... Sorry, friends. I'm running into... I think Leetcode was giving me weird things. Don't want to go over that one yet. I thought it's this one. Let's see. Yeah, it's this one. I don't know. Did I just misclick? Maybe I misclicked twice. Is that it? Okay. Well, in any case, so the query we did talk about, right? So, okay, just revisit that. But then here we have to process the prefix sum for the intervals. And the idea here is actually, honestly, pretty straightforward. It is simple, but not easy. Put it that way, right? Like, it's understandable, but not easy to do at all. And the idea here is really just keeping track of everything. It's not that difficult per se. It's just that you have this prefix sum, and then, you know, every time you pop from the stack, you pop from the prefix. But then you also get the prefix sum from the prefix, from the intervals, right? So this is the previous prefix sum. We wanted to add the existing prefix sum to it, but subtract the previous prefix sum, right? So what this is saying is that if you want to bring back up the visualization real quick, what this is saying is that as we are processing from left to right, so I have so many windows, I have to find this one, is that as we're processing from left to right and popping stuff off the stack, right? So okay, so let's say let's go back to the processing step right now, right? So okay, so let's say we have this interval. Let me just draw it from start. Okay, fine. You know, we have a stack. We have this interval. We have this interval. We have this interval, right? So then now, let's say we have a big number and we wanted to, you know, we have a big number and we're trying to eat this segment, right? Well, this segment, actually, I mean, I drew them like this, but you can also think about them as just rectangles at this point, right? We have some rectangles, right, as we kind of talked about, of various heights. Maybe this isn't accurate because it should be monotonically something. I don't know anymore, right? But in any case, but yeah, but you can also just have a number that contains this prefix sum, and so, yeah, so then now the idea is that, well, yeah, this should be increasing. So let's just pretend they're monotonically increasing, right? So you have this prefix sum number, right? So yeah. So then the idea here is just to get this rectangle. Let me draw another color. That's why I'm confused. So just to get this rectangle, you have to get what was the previous prefix sum minus the prefix sum one stack level before that. So that's basically the idea here for this part, right? So this t is the previous prefix sum. We want to add, and this is on a rolling basis of all the stuff we consume, right? So this is the previous prefix sum at that number. We want to subtract out, we want to add out. This is the new updates, right? Well, we're updating from the right index to the left index, each with a delta. So current is going to just, well, this is the stuff that we're adding to that box. And then here we want to subtract this out. Maybe this is a little bit less confusing if I wrote it this way, actually. Subtract out t minus, I think this is a plus actually. Yeah. Is it? I'm confusing myself with too many. No, I think this is right. I think this is a T minus. And that's just because this is the the previous sum of the interval calculated from interval prefix sum, right? Yeah. And this is of course the new addition. So that's all. We basically sum up all these components, and then at the end, yeah. And because we do all these subtractions, we want to add up. This here is just adding the previous interval, because now we're pushing something on the stack. So we want to take the previous stack's prefix sum and then add it to all the. Because current at this point before this, current right now contains the sum of all the intervals we ate, right? And then now current is now a prefix sum, right? So that's basically the idea behind this, because this is the biggest, the total of all the prefixes. And then yeah, we put it on prefix sum, we add it to the stack, and honestly, technically you could use one stack. I think I didn't mention this, but I just wanted to separate out my head logic because it's just too confusing for me. But you could use one stack, right? And here, again, you could do binary search on the binary search. So this is fast enough to get AC. We can even submit it right now because we made some minor changes with this, just to kind of show you. But it's very slow. Again, the complexity is still O of n log square n, right? So it's a little bit slow. Maybe another language. I actually, I think I had for testing. I forgot to submit it, but that's fine. I wanted to show the segment tree solution. I'm curious whether the original solution works, but I forgot to copy paste it. So okay, let's see. But yeah. But anyways, yeah. So this is a little bit faster than the other solution, which I guess we can do. Wait, let's see. Right. So I am curious whether the Java version works. So that's why I am gonna. And this is just off ChatGPT, so it may just be silly. Okay. So maybe I didn't need to make this update. Okay. Well, I don't know why this is wrong answer. Maybe there's some int long thing, because I think. Yeah, I mean, I think there's some int long thing that we have to fix, but wait, use long instead of int, please. Right? Let's see. Yeah, I think we have to convert this to long, because I mean, maybe not the indexes, but definitely query range, right? Give me a second. I mean, you're already like an hour in. This is a struggle bus. But I want to show you, like, you know, how to work through a problem, right? And maybe in theory, you probably could have done this a lot faster, but I definitely did not. Right? Yeah. So there was an int long issue. I do wonder if this times out with the segment tree. Okay, so it still times out the segment tree. Though it went further, so it definitely is more leeway, but it's still timed out. Anyway, but this would be fast enough even in Python, right? Sorry, this is fast enough even in Python. So anyway, wait, is this the right one? Okay, but so this is n squared log n, and honestly, if I didn't kind of was nudged toward it, I might have stopped here. But I saw that, and I give credit to Ace on my Discord for posting the solution. Maybe other people have posted, I don't know, but it's just the one that I came across because, you know. But I didn't really look at it that deeply. All I saw was, oh, n log n is possible. So then I just gave it a dot. Well, it turns out that the way that we did this, right, we didn't need to do this way. So the idea here is that, actually let me just redraw, right? So here, let's think about the binary search for a second, right? So the binary search, we have, the binary search, what were we doing, right? We're saying, okay, so this is the binary search, right? We're searching for a range, and then for each range, each query, we have all these segments that we have to binary search again to figure out the segment and then do a sum, right? So that's really what we were doing, and of course it was too slow. But it turns out that because basically here we have to we do this binary search, and then within here we have to first we have to do a binary search to find the segment. So then there are two binary searches, right? But it turns out that, and I gave this a dot, you could watch the live portion if you could find it, is that we don't actually need to, right? Because what is our function? Our function is just trying to get this portion is less than or equal to k, right? The sum of this is less than or equal to k, and the way that I did it is by looking at it here, right? But of course, if we look at this interval prefix sum in total, right? Like if we look at this entire thing in total, then we know that, well, and you should not do this in a linear way, but you know that for some amount, this is going to be less than or equal to k. And that means that here, what that means is that you don't need to you don't need to binary search through all the segments, meaning that, you don't need to jump around the different, you don't need to search for this index yet. You can just search for the segment. And then now, once you know the segment, you can binary search a second binary search, but now they're no longer nested. Because basically now we're saying, okay, because the first binary search now instead is just saying, okay, can we do it with 3 segments on the right side? If yes, then we can do it with more segments, right? So then now the binary search is on the number of segments, and then the second binary search is that, well, we know that it's going to be within here, then we do a second binary search within this segment to kind of add it in. And that's really the optimization that takes it from O of log square n to O of log n. And that's not the solution. How come I have so many windows? I think I get confused. Okay, I think this is it, right? So, yeah. So, now I didn't change anything about the prefix. Everything about the prefix is the same. The only thing that I changed is the query, right? So now, I have this part, we query for the chunk that we are in, the number of segments that we care about. And here, all we have to do is binary search on the prefix array. So this is a regular binary search. We try to find, basically, and I'm going through this way quickly because, it's binary search, and this is our problem. We want to get the most segments starting from the right side, from the processing node, that we can use without going over, right? So that's basically what this does. And now that we got the most segments that we fit in, without going over k, then now within this segment, and then here it's within this segment, do a binary search to find that k, right? Including the prefix sum we already did, prefix segment sum that we already did, right? So here we know that we want to, so the current total is just total minus t. So total is the prefix sum of all the intervals, right, that we talked about, and t is just the the prefix sum of what we binary search on, right? So that's basically the idea. So current total will represent current total is the prefix sum of all the intervals that we cared about, right? And that's it. Right, because then now this is the thing, and this is the same formula kind of as before. Not gonna go over it again, but it's the rectangle visualization that we talked about, because I don't have time to repeat things today. But yeah, so this is the area of the deltas. So the current total minus the deltas. If it's less than or equal to k, then we do a binary search. And then now f is just the index that we care about, right? So yeah, and f is actually the real left side of the thing. Actually, we don't even care about this. I just kind of did this for checking. But f is the index that we can that we can extend the farthest. So this is the number of elements at the end, right? You have the border is the element that we're caring about now. I call it border, just like the right border. And then f is, I don't know why I call it left anymore, but the left border. So then you just have this many elements, right? So border is the right index, f is the left index, and then it's just the number of elements, and then you sum it all together. And now, because now we do two binary search instead of nested binary search, this is O of log n, and of course this is O of n, so this becomes O of n log n, right? So this is going to be very fast. If you look at my submissions, right, just going to go really quickly. If you look at my submissions, this is my original segment tree Python n log square n. I did the optimization a couple of times to make it to use the stack, the prefix stack, right? So it's fast enough. And then, wait, which one is this one? I'm so confused anymore. Oh yeah. Oh, sorry. This is this time is the one where we remove the segment tree to use the prefix sum, but still two binary search. This is with one binary search, and that's the idea for this one. And yeah, so this is a way to do it for sure. But as you can see from the spoilers, someone told me that you can do it in linear time. A hint, and I give this props to Joseph and also someone on the leaderboard that I forgot, so my apologies for forgetting. But just to know that it could be done in linear time, I went to do it again. And the hardest part, and why I didn't discover this, is because honestly, I said this in the beginning, right? I was analyzing it from left to right, but from right to left, there are properties that I thought was wrong, but now is right. And that's basically it. Yeah. And I know that I spent an hour going over all the other solutions, but I really wanted to, go over the journey and the process, and that there are multiple solutions. And and these solutions were on the leaderboard, so you're all going to see them, but also it may come in handy in other cases. Who knows? But I just want to go through them. But yeah, in this case, it is just, honestly, a very easy sliding window. I'm going to show you the code just because, and this is going to take advantage of not the stack, but a queue. And this is actually a mono queue. So, honestly, the queue part is the mono. Some part of the mono queue is very familiar. This is very similar to what we did before with the stack. And the only difference is how we remove items from it, right? Instead of binary search, we actually remove things from from left and right. But cost, the idea here is that total is just the answer, left is just sliding window left, and cost is the total cost inside queue, right? And with that, if you're able to maintain this, then this is a very straightforward, simple but not easy, simple but not easy thing, right? Invariant implementation, right? Okay, so then now you have, And everything I've said before about intervals and the structure is the same, except for that now is a queue. So here we have the X we can name the three things. We have the X, we have index left, index right? And here we pop because we want to make everything in that interval bigger. So we pop, we make it bigger by, well, this is the delta for one number. We have this many numbers for this interval, so we add it to the cost. And again, we do this leftmost thing, right? Because we're consuming it, we already popped, so that we can do this in the future. And we don't even have to care about prefix sum in this one. It is kind of very funny in a sad way for me. But in any case, yeah, you just have the X, you have the left interval and the right interval, and that's it. That's all that represents everything, right? And the invariant here is that now, after we append it, cost represents all the sum of all the intervals we care about inside Q, right? And then this is the sliding window part, right? While cost is greater than K, we consume one from left. And then this is just the interval math, right? If the right side of the interval is less than left, we pop off. Shouldn't happen more than once because you can only remove one interval at a time. But yeah, and then Y is going to be the X, the Y of the value of the interval, and the cost is that we just remove. So the key thing to note is that we're removing one number at a time, and because everything inside that interval we convert it into X, right? Effectively, or in this case Y. So here, to remove one element, we just have to remove one element, and this is just the delta. Num sub left is the original number, and this is the new number, so then the cost we subtract from it. The hard part is now just keeping track of the interval. And now the interval, we actually have to update the interval inside the queue. I made this in a way so that is, so that I could just increment. But honestly, you can maybe even, like if you really want to do the immutable thing, you can actually just do a pop left. You can always do a pop left. Maybe that's the cleaner way to do it anyway. So you have Y, you have previous left, previous right? As you go to this, we have Y, you go to this. Then now previous left increment by 1, and then Q dot append left, append left. We want Y, P left, P right? So so you want to write it that way just so that I think it's a little bit cleaner, honestly. Submit just to make sure that I didn't make any silly mistakes. But yeah, and the reason why this is necessary is because if the next number we want to, the invariant here is that every interval gets increased in the future. So if if this number does not update, then here this may overcount. This may contain an interval containing numbers that are not in Q, right? So that's why we have to do it, and that's the tricky part. And it's kind of, I don't know. Looking at this solution, and it still took me a while if you watch the live portion, but looking at this solution, and or even, if you just maybe look at my submission timing, like it still took me half an hour to go from, go from here to here, maybe, I don't know. So even knowing that there's a linear solution, it still took me half an hour. So this is not easy. It is simple to understand when someone explains it to you. But yeah, and you can watch the live portion to see how I struggle with this one to kind of figure it out. But this is just regular the sliding window things, right? And this is just the window, the size of the window, and that's it. Yeah. Whew. That is all I have for this one. Let me know what you think. This is a very long video. I hope this is helpful, especially the process. Not many times Larry's gonna have a 5-hour video, so it is what it is. But yeah, you could watch me solve it live in a contest now. Maybe sillier if this is wrong. So, okay, how many people got this one? 91. I should have gone down earlier. I just wasn't thinking. I was trying to speed it up. That's such a new mistake. Okay, focus. Q4, let's go. We have about an hour left, so yeah. K operation, N is 10 to the 5th. Okay, and K operation, and okay, well, increment any subarray by 1. Is there no mod on this? It is long. That's actually maybe interesting. I feel like they should have added a mod on this just so that it fools people, because I don't know why that isn't the case. The number of subarrays. Actually, I misread that one. Maybe the n square is fine. The long, but should have still used mod. I don't know why you wouldn't. They use subarray in 2 different places, but yeah, okay, fine. Oh, for each subarray, you have to do it. So this it's for each subarray you do it and then you calculate. Okay, that is, I don't know. I wish I didn't spend so much time on Q3 because I don't know if I'm getting this one. Oh, leaderboard books again. Not great though. That was a silly mistake. Oh, we already done Q4. Okay. Non-decreasing 10 to the 9. So we can't do coordinate compression, at least not easily. Contribution. How would you do contribution on this one? Oh, these cannot be done. I think that's a, I don't know, that feels like that's a hint in the opposite direction. They're trying to fool you. Okay, so what can be done, right? So, okay, 1 of each array. Okay, size 1, size 2. This problem is too weird. Size 3. You got in 10 minutes. Wow, I spent 22 minutes on Q3. Jeez, that really was a silly time. I think focus on Q4 now though. So these are 6 and now 3. And then 1. Oh, subarray. Oh, snap. I thought subsequence for some reason. Okay, subarray. Okay, maybe then maybe, okay, focus, Larry. Oh, geez. Subarray. Okay. I mean, I knew that I read it, but then I think my head didn't parse it right. Okay, so then contribution makes sense, more idea. How do we do it? So then 1, we want to say, let's say we at 1, right? So you binary search all the possible things and then you do a prefix something. Okay, I guess that could make sense. Okay, that's tractable, I guess. So 6, okay, so 3, so then now, Okay, I see. Okay. This is doable. Subarray, not subsequence. Silly Larry. Okay. So then maybe, okay, for x and nums. We want to, maybe, I don't know, just sort the list for now. I don't know what I want. Okay, maybe, right. So then now, okay, and then total zeros. And then now for each number we go, we want a binary search. Maybe k is not the right number, but okay, so k is the, okay, so how do we want to, we have k left, right? So then the first number will be trivially true, so just, let's just say 1. Do I just care about the delta? I guess I only care about the delta, right? So then now, so maybe I do this. What's it called? Pairwise. Previous and x, and then delta is equal to previous and x, or previous minus x, previous minus x, because if that's greater, okay, actually I guess we could just use an if statement, right? If p is greater than x, or if x is greater than p or equal to, then we're good. So total, we just add length of SL and then we continue, right? Otherwise, then now what do we want to do? We want to say delta is equal to p minus x, right? And then now we want to subtract this from every SL. Right, okay, so then we want to do something like this. Okay, it's some idea of prefix sum and then binary search or something. I guess that's really it. I'm making it complicated. I think we can just binary search for prefix sum, and this is pretty straightforward. Or even with sliding window, really. Yeah, I don't think this is so bad. I don't know. I'm just surprised not more people got it. I guess people are getting it. Because basically it's just prefix sum of the deltas, right? So this is 3, this is 2, so this is 5. 5 is good, and right? Oh, this is not the delta from that. It is, oh wait, no, that's wrong, because it's not delta from the previous one. It's delta from the highest one. Okay. So maybe binary search makes sense. We just have to figure out how to do the maths. Okay, so it is harder than I think, but with an hour, 50 minutes, we should be able to do it. Okay. How do I do that math, right? So this is delta. It's not just prefix sum on the delta. Okay. Also, prefix sum on the delta would just be the delta between two elements, so that's dumb. Okay, visualization. Visualization. How do I calculate the sum of that? So then the delta is just the max of the 3 elements, which we can find with binary searches or with segment tree or something. And so the max of the 3 elements minus the sum of the 3 elements. Okay, that's not bad, right? Prefix sum we can do easily, segment tree we can do easily, right? Okay, let me find my segment tree things. Is that fast enough? And we can even actually do RMQ, right? We don't need segment tree. I have that written somewhere. Where do I have it? It's fine. I think we got this. It's fine. I'm just taking the time because I'm slow. Okay, RMQ. RMQ, and then prefix sum is easy. We want max. And where's max? Oh, we do F. Where's F? Oh, self.f, self.f. I think we want actually L max. Yeah. Did I call them? I call F max actually. Okay, so actually, okay, I misread the problem. So I'm Q of nums, right? So okay. Okay. Should runs. Okay, I'm Q runs, and then now basically. Yeah, this is just sliding windows, right? And then prefix sum. Right, okay, and then now we can actually do this now with regular contribution stuff. Oops, what am I doing? What is going on with this UI? It's just me being stupid, but still. Okay. Okay, so we want to say at the end we want total right, minus stuff plus 1, right? Something like that. And then left is going to be, yeah, we want to include what, right? And then now, so we want to say, okay, the length is going to be equal to right minus left plus 1, right? The height is going to be equal to max. So Q between 0 and left and right. Maybe I don't need to set. Right, and then sum is equal to prefix of right plus 1 minus prefix of left. Yep. Okay, so then now we have a while true statement. It should be a do while statement really, but maybe I could do it in do while way. And then now I have times height minus s is less than k, is greater than k. So while this is true, we increment this, right? And that's it. I think we're done. Oh, well, this is silly. If this is true, else break. Okay, I mean, we're mostly done, or was mostly done. Maybe now we're more done though. 17 and 10. Ooh, 10. 10 is no bueno. Whew. Okay, I mean, maybe we have some silly mistakes. Hopefully not. Print right, left. I mean, we're close to done, so I mean, we have 45 minutes. We should be okay. Hopefully, 0, 0 is 1, 2, 6, 3 is 2. Okay, 2 and 1. Yep, that makes sense. 3 or fewer elements. Did I misread the problem? Increment any element of the subarray. Okay, yeah, no. How is 4 enough for this? Oh, they say 3. No. That's not true. 3 or fewer elements. Oh, except for this one. Okay, fine. I didn't read it. Okay. Okay, 2, 1. Okay. 3, 1. Okay. Oh. I forgot that it has to be non-decreasing, right? So this is actually not right. This is only right if... okay. I have to think through it again. Okay, we're not done. We're not close to done. Because okay. The idea is still right for decreasing. If it's increasing, then we don't change it. Is that how? But then the math could be wrong. We only care about it if... this isn't right then. The invariant is that this only goes up, but then now you have to do the math on the decreasing side, right? Okay. All right, you have 45 minutes. You still should have time for this, but not so bueno though. Okay. I see. I misunderstood some parts of it. Okay, it's good that this was wrong though. Well, I mean, it's very hard to be right on this one, but... So then, okay, so... But this still requires... Okay, so... Okay, so this is still true, right? So it's not, but it's not the biggest element. Because then now we could have something like... And that should actually be, you know, a trivial true for everybody. Well, maybe not actually, but we're definitely 136. Okay, so then now. So only if we decrease is the number, right? So we would get the max, but the location of the max as well, right? The leftmost max. So then now you break into 2 parts. No, because then you could have like a longest increasing subsequence thing. So that math is not sufficient. Okay, but let's say you pop off. Okay, so I think this is a little bit lazy, but I think we can make it right. So then, okay. So then current max is equal to 0, right? So okay, so then now at the very end we do current max is equal to max of current max and right. But and then now here, if num sub right is greater than current max or even equal to, then we are good. The thing is, once you pop off the max, then what? Then the cost is different, right? Okay, so maybe I have to do something like the way that I'm doing it, but actually maybe I don't know how to do it. Only 20 people's gotten it, so maybe this is not it. Because then okay, because then okay, huh? Not a good. Because then now going from 6 to 3, then the one cost is different, right? Okay, so maybe it's not just getting the max value. So this 3 does require a 6, right? So then now so we do need a sorted list maybe. Then how do we get the cost afterwards? Okay, Frank. Okay, let's say we have a sorted list of 631. We have the cost, we do the math. We go, okay, 1 add 5, right? And then now it's 6, right? So then now okay, I think it's just maths. I don't know that I need the RMQ, but I guess we'll just keep it there for now. Remember to remove it, Larry, or even the prefix sum, really. Maybe we're back to the sorted list. I'm going to copy and paste this. Actually, I'll just open a new window. Okay. Right, and then now you have the total number of arrays, right? And then, okay. Let's just say total is equal to 1, make it easier, and num sub 0. And then now, yeah, left is equal to 0, right? We start 1, and then we want to add, right? Okay, so then first we want to get the max element, right? Minus num sub left, right? And so sum is equal to num sub. Okay, I think the same idea holds. Okay, okay. It's just that I have to think about it. Okay, so then the max is okay, so delta is equal to this. If delta is greater than 0, or SL sum, we add it by num sub right, not left. What are you doing, Larry? And then if delta is greater than 0, then cost is equal to delta, right? So cost is also 0. I think I had, okay, cost is equal to 0, right? Okay, so then now while cost is greater than k, we want to move left, right? So we want to do SL dot remove cost. Is that how I don't sort the list, remove element? I think that's right, but I don't know if it removes all of them instead of removing just one. Do I have to bisect? Oh, remove? Did I do remove? Yeah, let's just try dupes instead of asking, right? So then here, maybe, whatever, right? So there's this one. In this not iterable. $31. Oh. This is also remove SL of left, but okay, fine. Whatever. I just want to test something. Stop it. Okay, so SL dot add 1, SL dot add 1. I just want to make sure that it doesn't, because in some libraries I'm confusing which ones they remove multiple versions, and then that's not great. I think C++ might do that. But anyway, okay. So then now of course right, left increment by 1. But then now we have to update the cost, right? So yeah, cost. So SL sum subtract by SL of left, right? And then now cost is just equal to the max, which is this. Times the number of elements minus SL sum, right? And that's it. Well, have to increment left. Okay. Left is our bounds. Cost is wait. Why? Oh, not SL of left, nums of left. Okay, so SL has 0 elements, but that shouldn't make sense. Honestly, this could just oh wait, no, this is still having the same issues that I was talking about because you're popping off. So I have to do a little. Because it's not, because then before. No, this is wrong, this is wrong, this is wrong. I mean, we still have to fix whatever this is anyway, but it's wrong anyway. And maybe that's why that's wrong actually, but I don't know. Because if you have something like, I guess just even this input, you remove this 3, you remove the 6, then yeah, you get the max, but that's not the sub thing, right? The sub thing is you subtract its contribution, but what is its contribution? and then you have to figure out how to do the math with 3. Maybe I don't know how to do this. This is ridiculous. For me, I mean. Okay. Yeah, I'm doing the same thing, but that's wrong because of the same reason. I don't know how I could do it, but I mean, basically, I am doing the same thing with the literally. So I'm having the same wrong answers, also literally. Even if I fix this, this would be wrong on here. No, I mean, I think I fixed this edge case of going up, but then once you reset it, like if it goes from 313 and then maybe if you have 312 instead. I think I forget to add nums away, that's why. But then it still doesn't make sense though. I don't think this works. I mean, it's just wrong anyway, but because then now you have to do with the thing, right? And then, like if you have something like 6 1 1 2 3, if you remove the 6, so sure this has a lot of costs for these, but if you remove the 6, this actually becomes 0. So this doesn't work, right? So how do I make it work? The idea being that, of course, you have a 1 here, right? Okay, so if I was fast on Q3, I would feel less sad, but it is what it is, I suppose. Okay, so then the idea then is that when you, okay, so you have a stack, because, okay, you have to do a mono stack on top of this. Okay, I think I get the idea, but then it's just the longest increasing sequence. So then now you remove them one chunk at a time, right? Because they don't contribute to the cost, right? Okay, so maybe I could bring back the armQ real quick. Maybe. Okay. I think this one is easier to work with. Maybe, actually, I don't know if that's true, but well, I mean, this one doesn't work. This one's a little bit good. Okay, let's see. Okay, so we have this one, right? So, okay, so we have So how do we get the new cost? The new cost, we don't have to calculate the new cost for, actually, do we? Okay, actually, no. So the new cost, it's not this thing. New cost, we just subtracted by the thing, right? Because for every item, by definition it's going to be smaller than it. So every item to the right of it, right? Which is, with all on the left, then it's going to be every item. Okay, so it's not this. It is the max, or the previous max, say. Previous max is equal to SL, and then now we remove it, and then now the cost difference is going to be minus this, the new max, times the length. Does that look right? Yeah, I don't know how didn't I fix that? Okay. But do I not increment? How does this work? Is that wrong? No, I guess we just don't add. Okay, we have 20 minutes. Maybe I get it, maybe I don't know. It's kind of hard, but okay, so 0, 2 is 8, right? So 3 plus 5, okay. 2, 1 should be, which is too much. So then now 2, 1 should be 2. What am I printing? Where's my print statement? Oh, I increment left twice, which is silly. Yeah. Also, we don't need SL sum maybe, but Alright, 1, 2, 5. Okay. Now you remove 1, and then now we have to add this first. No, that doesn't make sense though. Well, what is the cost? 1, 2 is 5 is wrong. So you subtract this. So you added the 1. So this only goes up if whatever. So I think this is fine actually to be before. I think that's where I messed up. Okay. Is it right? I don't know, to be honest. I have 24 minutes left, so I think this is good time to take a YOLO. So let's YOLO. I wouldn't be surprised if it's wrong. I just want to get a quick right wrong answer and figure it out, right? Okay. Okay, so 3 is 16. Okay. We moved to 11. Expected 9. So what's 9? 4 choose 2. What's 4 choose 2? Is 6. Right? So how can it be 9 or even 7? 4. Oh, it's not 4 choose 2. It's 10, right? 10. So 9 means that there's only one array that's not possible, which is all of them, right? So then now went from sum is equal to 16. Oh. So, okay, so there is something wrong because this actually contributes to 2 to the answer, right? Maybe this is wrong too. I mean, it is clearly wrong, but we have to figure out contribution by itself for each number, right? So if this is max, if this is the new max, I don't use this, delta mf cost is equal to the max minus but then we have and then we want not just this, right? So then here, okay, fine. Let's run it real quick just to make sure I remove the right things. We have 22 minutes. I think we're okay actually. Yeah. I mean, we could do this anyway, but 0, right? And then contribution is equal to, I don't know, whatever. I'm being lazy with the thingies, but I guess it could be a lookup. Okay. So if delta is greater than 0, okay, so let's save that a little bit, right? Right? And current max index, contribution of current delta, right? And then now, yeah, if current max is less than num sub right, then num sub right is current max is equal to num sub right, current max index is equal to right, and then we add. I don't even think we need this honestly anymore, because then now yeah, we just subtract by contribution of num sub contribution of left, and then that's it, right? So we don't actually even use sorted list really. Let's just run it real quick anyway. Previous equal to well, we don't add it anymore. Wait, do we? I don't know. We don't use it anyway. Huh. Yeah, okay. Why is this wall? Cost, because contribution is 0 for all of these for some reason. Oh, if it's equal to right, we have to update if it's equal to right. That's right. I had this in my head, but then I forgot. Does that mix it? Nope. Okay, 0, 2, okay. Whatever, the sorted list don't matter. Okay, that's fine. 0 to 2, that's 8. This 2. Oh, this is wrong, isn't it? Because then now this 2, even though it has a contribution there, but then the contribution is a stack, right? So then now the 2 actually has contribution to the 3. So maybe I won't get it. I knew that this was, well, I knew something like that was somewhere, but I couldn't figure it out. Because then the 2 now contributes to the 3. And how do you do it? I mean, it's a mix of kind of what we had, I suppose, but it's the contribution all the way to, right? Okay, so and the contribution would be in a range. So then contribution here, maybe we say is equal to right, so it's an index instead, right? So then now, in this case, did I get the wrong answer? I mean, did I submit it? Was it this one? I actually don't remember. I think I really reused some of this. That's why. Also, we should remove the Q code. Yeah, okay, so we have this. But it's okay, so I only care about this. I think this is the key. So then now we remove the left, and then contribution of left is the rightest moment that it went to. Something like that. Well, not like that. It is something like that though. 9, 3, 3. Okay, not subtracting enough. Oh no, it's not length of SL. It is, so that's the width. Then the height, it's actually, and I need to update current max, so I do need a sorted list. I lied about not needing sorted list. Yeah, actually that makes sense. So then it's just going to be this, right? No, that's the width. So then it is previous minus SL minus 1. Okay. Okay. We don't need the sum though, I don't think. Okay, where am I out of text? 856. Is it the length? Okay. No, just give it to me. 4, 4, what? Of course, this 8 is wrong. That means that it's not subtracting enough. Is this plus 1? Okay, so if this is true, then punch. Let's update the thing maybe. Okay. It's still wrong for this one though. So, but at least we're in a good. I don't know. It's a different place. We're in a different place. Let's remove RMQ. It doesn't seem like I would need it. I have to figure out how to keep this. Okay. So, okay, 11 to 9. Okay, so this has to subtract, right? So what is the contribution of left? Two. It's to 1, right? So 0 to 1, left to 1. So this isn't right either. This is this is to the next big thing. So basically if there's a new max, well, this is trivially true, but then basically it's just to the next number that's bigger, right? Next number that's bigger or equal to. So this contribution to the thing doesn't really need to be no, because then you have like 634 and then you have like, okay. I don't know, maybe I just don't know this one honestly, because I have this case where it is like I don't know, 6 3, I don't know, 1 2 whatever, and then 4 and then 1 2, and then now in that case these will have a different impact than these, right? Maybe I should have done this. I don't know if that doing it backwards change anything, but maybe this is just too hard for me. Please, no comment. Okay. Oh, this is the wrong. So then how do I get this, right? So the 2. So, okay, maybe starting Windows is not the way to go, I guess. Maybe I tried too hard to make it work. Yeah, because here, when you remove this one, how do you get all the sum of this in one? Right? Is it a segment tree thing where you... No, I mean, can't really do this in... Even with a segment tree, like you said, effectively, you're still doing a tournament, and that doesn't make any sense. Because it depends on the range, and then now... I guess maybe it could be segment tree, but it's too late to implement, I suppose. Because then you just combine it on the previous number, but maybe, I don't know. I think this is the case that I don't know how to figure out. Let's give this 4. I think, well, the thing is that after adding it in, the 1 and the 2 never matters anymore, right? Because so then you merge, let's say you do some merge to 6 3 4, then what happens? And then you merge the 3 to 4 as well, actually, technically, right? With a lot of maps, maybe? I don't know. The increasing stuff we really don't have to worry about, but then we priced it into here. I think I'm okay. So let's say you have this thing, right? Well, going to the right, it never matters again. but then if you remove the 6, the 3 may matter. We moved. That's the part that I don't know, right? So then, okay, say one currently adds its contribution to a range, but it doesn't even, right? So let's say if there's a 2 here, then 1 does not care about the 2. So the 2 could, well, if 2 is behind another 3, right? So then you remove the 6, then the 2 actually cares about the 3. So I don't know. I'm at this point, I don't think I'm going to get it during contest time, with 6 minutes left. But I don't know. I feel like it's one of those problems that I feel like like maybe I could do 74 people, but maybe today's just not the day. I spent a lot of time on mistaken things. Yeah, and I forget, I lost the case, but that's fine. I think it doesn't actually, I don't think I'm going to use it, and I'm not going to get in the next 6 minutes. So I don't even have a realistic idea. I think there's some like mono stack thing, but 6 impacts all these numbers. But how? Like it's like almost like each number has a mini stack. So 6, we want to subtract all this, and then also the 3 with the 4, right? Which is a little bit awkward. And then this, of course, will get merged with this, I suppose, but 1 is also contribution to 3. There is some like property here that I feel like it's a stack problem, but I can't really place it yet. Of like, oh, there's a stack, and then I don't know. It could also be that I'm doing sliding windows wrong. Maybe I'm doing sliding windows wrong. Let's say we have starting with this and going to the right side, right? That is something that I didn't think about. And then now when you remove this, what happens? Oh, you have all this structure. I mean, it's the same problem, right? So maybe it doesn't change that much. I think the sliding window is about the same idea, implementation-wise. If my Q3 wasn't so silly, it would have been good. But yeah. Like on a good contest or decent contest anyway. I don't know if it's good, but today I did not pull the rabbit out of the hat in last minute magic, but it's basically saying, yeah, because here when you remove the 6, how do you do this operation in good time? Let's say we have a fake we put, right? So, and then now it goes to right? So that's the actual thing. How do we represent this? Is it a data structure thing, or am I just being silly? Well, I guess there's no 6 in this case, but You can't really store everything. Maybe there's a reduction to make it a simpler problem. Instead of divide and conquer, like a merge in the middle thing, right? On divide and conquer. No, then you just have to do like some n square merge properly. The thing is that ordering does matter a lot. So that's why the sorted list is not really the right data structure. I really don't know how to do it. Terrible contest aside, but it is what it is with contests. Yeah, I mean, there's a minute left. I'm not getting this one. I'm going to try to upsolve this. So I'm not going to try to avoid some spoiler. I mean, maybe I'll take a hint at some point, but not yet. Definitely subarray is easier than subsequence though, so yeah, not a good content. Oops, not force. How do I go to this state from this state? Is it sliding windows? Is it a query problem and I'm just messing it up? I thought. I don't know. Maybe it is a crazy data structure thing. Was anybody get it? Like I think this case is why sliding windows won't work. So like I can, or like how do I do this in less than of n times, right? Because you can get, from this idea you can construct an n square case. Though I don't know, maybe that's not true. In that, like, maybe it's amortized, right? Like, I feel like maybe I didn't think about amortization enough, but I don't know. I don't know. Maybe I could do armq, but not this. The idea was, I guess, sparse table, not armq. How would, if I had to combine, then you could get the sum that way, right? With sliding window, then you just kind of, instead of to the query, this would get you the max. But what is the combine, right? This is the combination of I forget which version of the thing I'm doing, but no, I think this is fine. Right, so how do you combine left and right? Then there are most log n copies, and then sliding window would work. Maybe that's the reason. Okay, that makes sense. Then the f is not f, right? Then f is we want to get the max, so there'll be two of these. We want to get max. I don't know. I mean, I feel I have some idea. How do you do them? Like, how do you do a merge of two halves? So then you want the max, but then it just becomes like such a weird merge. I'm gonna take a peek. I don't know that. Seems like the prefix sum. Yeah, well, binary search and prefix sum. So no crazy algo. I don't know. Okay, maybe I'd have to. Maybe I just don't know some maths. Like I don't know what this form. I mean, I guess it's probably very similar to what I'm doing, but going backwards. Does going backwards make it easier? Maybe going backward makes it easier. I don't know that I thought about it. I thought maybe. I thought it would be I thought it would be symmetric, so I didn't really think about going backwards. Let's actually, because I was a little bit too slow in it, but okay. So let's say we are going about it backwards, right? Let's say we have something like this, and then now we want decreasing, right? So we score on the next number that's bigger, right? So maybe that's easier. I don't know. Because then now we have 2 and then the one we don't care about. Well, now we have 2 and then the 1. But then when you see the 4, you have to process. You have to process the thing, right? Well, here then now we know that we have 3 in total. We have 3 in total, right? We see the 4, and we have, well, a 2 with, so that means that this is 6, and then you could get, yeah, so 6 minus 3, so the cost is going to be 3, right? Okay, so the cost is going to be 3 for this thing, which is fine, we know that. So then now we have a 2, which costs us nothing. Right, 1 costs nothing, 3 costs nothing. Well, no. Okay, and then now you pop that stack or whatever, because those cannot affect you anymore. So we could calculate this way for contributions. But what if there's what if we started this way, right? 6, and now we have we go 2, we go 1, we see a 4, so now 4 is bigger, so then we pop, and then now we have a 4, and then, but then how do we get the cost, right? Oh, the cost is 3 because the 4 and the 6 don't interact. Okay, so then now the 2, but let's say 2 is now too expensive, right? Then what happens? Then you remove the 6, and then the 4 is okay, though you have to count the left boundary of the 4, right? And then we have a 1, and then we have 3, and did I just not think about it backwards? That's like one of the first things that I tried to do, but then I even talked about it, but maybe that's it? Is that the idea? That is easy. I just, for some reason, I think I didn't mentally consciously realize that it is asymmetric. But yeah, all right. Well, maybe I'm just being dumb then. Maybe that was the only thing. Yeah, maybe that is. Because then now we have a mono stack essentially, right? Is that true? I don't know if this works. I'm just Okay, 6, we have 2, 1, and then we have a 4, and then the 4 yeets these, and the 4 can yeet these. I mean, I did the math with the range query, but I don't even need to. I feel like this is wrong though, but I'm just like not thinking about it well. How did I, I'm trying to see, okay, there we go. Okay, let me at least play around the one example that they did give me. 15, right? So then now, let's say you go backwards, 3, 17, 17 yeets to 3, right? For a cost of 14. Yeah. And then 9, which is good, and then 11. 11 tries to eat the 9. But then this would be 15, so then now we pop the 3, say. We pop the 3. Then we just subtract the 14. Is that enough to fix it? Like, is that really, like, it's just mostly this code but backwards, right? That can be, but okay. I don't know. Is it not more complicated than that? Maybe okay. Maybe that's why enough people got it. But yeah, let's see. Yeah, so maybe num start reverse, okay, right, and then now, did I have a copy? Let's just open other groups, another copy about this. Yeah, I mean, I didn't, yeah, I know, I looked at his code kind of, but I'm also like not, because I don't know. I just wanted to see if there's some like crazy data structure that I didn't know about, and you know, that was it. And I want to, you know, because I still want to upsolve this, right? So that's the main purpose of what I want to do. So maybe I just paste this here, right? So then now, okay, so then left is equal to 0 for right in range of n, right? We want to say, okay, well, so we have a stack kind of, right, of numbers, right? So then our length of stack is greater than 0, and we want to, yeah, okay, stack -1. So the top of the stack, we want to store the well, store the number, but what else do we want to store? I guess that's it, really, right? Oh, and the count, I suppose, because it eats out the numbers, so those numbers would have to be cleaned up as well. But I guess that's the thing, right? Maybe I didn't get this right. Maybe this is still well, because then, you know, you have, say 1, 2, 3, 4, 5, and then now this is in reverse, and then what? Because then now 2 eats 1, right? So the 1 contribution is actually, so when we remove 1, the contribution is only 1. But no, because the contribution is actually 4 from here, right? So then, okay. So maybe that's where you need segment tree, but they didn't need a segment tree. Maybe they had some other query though. Let's see. I just want to find out if there's an easy way of doing it. Okay, so that prefix sum. Okay, so actually, okay, I guess they did do the same thing I did, but I guess they did the formula a little bit differently. Because then now, oh, they do binary search instead. Huh. Okay, now I'm definitely cheating. So okay, so what I was going to do wasn't going to work, at least not in this way. I was thinking about going from left to right, and then just figure out how to remove this one. This one has a contribution of actually 5. How do I determine that? Right, because 2. Okay, let's say every time you yeet, you just add the contribution here. So maybe lazy segment tree. I don't know. I mean, I don't know if that's a crazy idea. Do people use segment tree? No one uses segment tree. So I don't know. Like I feel like okay, because my idea here is that okay, well, anytime you yeet a number going from left to right, so like 3, we yeet 2, but 2, you know, that has a range of from 1 to 2. So then you can just add that delta, right, to 1 and 2. So then when you pop 1, then you just get it. Right? Maybe you could do it in another way, actually. Because okay, so okay, when 2 eats 1, I think this is possible actually. Let me just write it. Let me. I mean, maybe it times out, but I want to. I think correctness wise, it should be correct. So I want to. Yeah, I want to do that. Okay, so stack contains nums and index. Is it nums and index? No, it's x and index. Or left index, right index maybe. Just the range that it represents. I think that's fine, right? So then now the 0 element is less than the current num sub right. Say x is equal to num. Then we want to do pop, right? Except we want to yeet it. So here we have previous x, left right index, right index. And the right index doesn't actually matter. No, I mean it matters because of you want to get the length. Okay. Okay, yeah. No, I mean not just the length, but wait. No, because that here, for example, let's say you have 3, 2, 5. So then the 5 eats the 2, gets the range, and then 5 eats the 3, also get that range. Okay, fine. I guess to keep it dumb, yeah. Okay, let's do what's it called? Sig Python sig tree range update value query. Okay. Not gonna lie, I am using ChatGPT, but that's only for code generation. Like I've had this somewhere. I have to find it honestly. Okay, up. Okay, fine. Right. So then now, right? So then x minus px. We want to add that. Oh, we don't want to update range. We want to. I just want to make sure that this is set as. Update range, propagate in. where's the... No, we want to add that for a link, right? Okay, yeah, I think this is right, actually. Okay. So then now we want to okay, sig tree is equal to just sig tree. Or segment tree. Times n, I suppose. Okay, and then now we just want to add, or I guess update range, whatever it's called. Left, right, so left index, right index this, right? And then leftmost is either right, and leftmost is equal to L index, right? And then we just keep doing, we keep popping. Okay, so then now we can push, so leftmost, the current index, and then just X, right? Oh, wait, no, X is the first. Okay, yeah. Okay, so then that works. And then now we have the cost, right? Okay, yeah, so here we have the current cost is equal to 0. So when we eat stuff, what does that mean, right? This is actually, no, that's right. So then now the cost be added by I don't know what that sound meant. I think I've lost, I'm muted. Is this right? Am I thinking about it right? I'm thinking, hang on. Okay, so I think the thing is that here, L index can be, yeah. I guess that's fine. Actually. No, is it? Okay, because basically here we are consuming on the right side, right? And you eat to the left to calculate the current thing, and then now, I guess now then we can do a binary search on the left side on the right to get the index, but then that's where you get the n log square n thing, and maybe that's too slow. Because then you just sum it up all the way here. Okay, I think that makes sense actually. But also I get only one element because I thought I could just slide with it. But with the query, with the binary search, then we need a range query, which is fine. We can change the template. Yeah, I'm just trying to think whether I want to do it that way, n log square n. I didn't think of it. I thought I could do it with a sliding window, but maybe that's not quite right. Also, I don't even know if that's quite right now, because if you do a... Oh, no, it's right now, because you could do a binary search now. You cannot go back later and do it. Okay, that makes sense. I'm trying to think whether I can do better than n log square, and I think that's why. But yeah, I didn't even think about doing this in reverse. I thought about it a little bit, but for some reason I just kind of dismissed it. So that's not great. But yeah, and now here segment tree represents all the thing. So then here we can do a loop, right? So then here maybe yeah, cost isn't a thing anymore. We can just say total whoops, get from the right. So then here we can just do something like get right bound, whatever, and then we figure out the left side, and you know, we can, for correctness, we can just do I see. This is where you can do the prefix sum and make it faster. Because on this, you would have a prefix sum stack almost. Can I do better? I mean, we could do a binary search on a segment tree. I think that's just not interesting. That's why I'm thinking about it. I mean, eventually, I think I'm just gonna come up with the code that we already kind of sneaked at, but I'm trying to like reason it myself. All right. Okay, so let's say we have this update range. What does update range means? But you can't really... You have to okay, but there are a lot of ranges that you can update, so I think that's part of the trickiness. But amortized, it is okay in theory. Right? Because once you yeet a number, no one else is going to yeet it. So then the idea then is well, the way that I'm thinking is still going to be n square or n log square n. Well, let log square n. But the constant's much better, I suppose, if you do it with some sort of prefix summy thing. on a bisection on the array, on the prefix sum. Basically, we have an array. But yeah, everything still like kind of is the same. I don't know. Yeah, I mean, let's actually do this, and then we'll yeah. Yeah. And then maybe, you know, because I think the way that I see it the other way is still n square log, or n log square, and then now here, what are we doing? Okay, so we want segment tree. So that, oh, we need a range query, right? Yeah. We have lazy propagation. Update range, query range. Okay, so now then we want to do query range, double check, mid border, right? So if this is gray, if this is less than or equal to k, then we're good. And what does good mean? Good means that we can try something bigger. So we want right to be equal to mid, else left is equal to mid plus 1. We want to try something smaller, and then we just return left. So then left is going to be yeah, just so left. So then yeah, border minus left plus 1 is what I'm saying. Okay, I guess this would kind of easy, but oh well. Multiply sequence of oh okay, fine. Total get by, do I not have a total? Total. Okay, right. Yeah, I mean, I don't know. I mean, this may time out, like, because that's what I was worrying about. But yeah, and that's fine, honestly, in the sense that at least it's not wrong. Yeah. But I think the part that I was struggling a lot with was that I had to think about it backwards, right? Because here, then now, maybe we could think about an optimization with the prefix sum, which is kind of what we cheated at. We can maybe close the other ones for now. Right? Because this part is too, well, I don't know, this is like, yeah. And then now can we do better, right? I guess maybe that's why a lot of people got the 5-minute penalty, but how do I do it that way, right? So then you need to do on a pop. How do I do it? I mean, at least like, you know, honestly, that makes me okay. With time limited, but at least I finally find the core of the problem, right? Like I should have been able to do this. And I don't know that we cheated that much. I mean, sometimes you have to be honest with yourself, right? I mean, obviously it's a little bit slow, but the only thing that I double checked was whether I need something crazy, and the answer is no. But I needed to do this in reverse, which for some reason I think that part is the part that I'm most upset with myself with not getting, because I even talked about it a little bit during the really long video that you're watching, the live portion. But yeah, it leads to a much easier thing, right? So this is tractable, and then the question is, can I reduce the log n? This is log n, that's fine, but this part is log n on log n, which is too slow. Right. I don't know. I don't know how to reduce this. I mean, I think there is some prefix, some maths that you can do as you're updating. Okay, that makes sense. I think the invariant is that, because I think the I think the thing that I worried about was that what was that if we're talking about numbers getting eaten, is that you have these numbers, and then like, okay, 1 2 3, and the 3 eats the 2 and the 1. Does it matter for the 2 and the 1? I don't know, right? But I think you can say that because the reason why 3 gets to eat the 2 and the 1 is because it never matters to any number the next, except for that it only corresponds to 3. So I think as a result, then now here actually maybe we don't need this, but we need to think about how to do it. Okay, so what does that mean for us though? What it means for us is that this number, of course, we need to hold all the sum of all the things, right? So maybe there's a certain t for total, and that's fine. I mean, maybe we can even be lazy and still use segment tree for now. I mean, could maybe optimize it out, but let's go back to let's go back to the just query one value, right? Is that what I want actually? Well, yeah, maybe we can just do st query range of leftmost, right? So we have this, and we have t. What does that mean, right? I guess this actually, I mean, you could probably like do a prefix sum on this to get this, but what does this mean for us? This means for us that, okay, so now we have another array that is parallel to stack, right? And we can, I think now we are able to figure out how to, okay, yeah, maybe. And then now we have a prefix array of just a tuple of, let's call it prefix, right, of all the numbers that are in between. So then index, because this is the Q4 from like 2-3 weeks ago or something like that, right? And we're just trying to figure that out, right? So then now we have the index and total, right? Oops. Right, so then here, yeah, maybe and then prefix.pop, right? Every time we pop, and then here, actually maybe because we're a little bit lazy, we can just do something like this, right? Maybe we don't need it here actually. Maybe, yeah, I mean the reason is because I think we want to do another thing to it, right? So every time we do this, we pop. That is going to be the sum. Is that right? So then it's just prefix sum then, right? And then now get, instead of querying the entire thing, now we want, instead of doing this, we want to go, let's call it query mid, because query, let's just put in a comment, right? And then here, query, I don't know, target is just going to be binary searching on the prefix array, right? Yeah, right. So then now we want to binary search on the target, which will get us the, no, it should get us the right one. No. It would get us the next one. So actually, maybe we want to do right left, even though it looks weird. And this is leftmost. Okay. So then now when we binary search, we should, okay, right? We want to search for the target. I guess negative infinity, or even just negative 1 is fine, right? Because we want, if it's equal, then we want that one. So this is actually, no, maybe this is fine actually. Actually, yeah, maybe this is fine actually. Okay, fine. Because then now, if it's equal, then it'll go to leftmost. And that means that this is the full one, right? So this is the full index. So this is the index that we find, and this is the full one that we care about. And that's where the prefix sum gets us, right? Because then now, the sum of all these things is just equal to the prefix sum. No, we want to query. So this is, yeah, okay. So this is actually from 0. So then we get the entire prefix sum, right? So then now we get the entire prefix sum. We go, okay, we have a prefix sum, right? So then prefix of index, and this should always exist, I think. I mean, it'll give me an error anyway, so, but it should be always be true anyway. So okay, prefix of index. So this will contain the left, right, and the prefix sum, which is fine. So actually, we don't care about the other two. So T is actually the immediate total, and then now the previous index. So yeah. So then if index is greater than 0, then we have the leftmost, or the previous left, say, the previous right, the previous total is equal to prefix of index minus 1, and then we have t, we minus pt to get the prefix of, am I doing this weird? Okay, so if, so we get all of all that stuff. Am I doing the prefix sum correctly? So then now, no, we want the previous one. So okay, so let's say we have 5. I'm just visualizing numbers in my head. So if it was 5 and we want to 10, then it would search, it would go to that one. You have to prefix some of that one. No, I think I'm wrong on this. So I think I have to go back to this. Okay, so then now, in this case, we will find it. And this is the partial one. So then the prefix sum of here is including this and okay, yeah. And then now we want to subtract it from the total, which I guess is actually technically here. Okay. Current total is equal to this thing, say, right? So then get current. So this is get total, maybe query total. Yeah, it's weird, but okay, fine. Total, right? So then the prefix sum is just minus t is equal to the current total is equal to this, but then you have to add in the little dinky, which is the previous index. So no, it's this index actually, right? Yeah. So then now it is going to be target minus, okay, so this is going to be I guess actually now that we write this where we need it, so previous right, previous left, so then it's target minus previous right, or the other way around. It's either this or +1. No, it's +1, I think, in the case that they're exactly, actually I don't know, I think this is right now. So okay, so it's this. So okay, so current total we added to this, and that's it actually. Yeah, so hard. Let's see if this is even right. I don't actually know what the answer with this one was. I mean, oh, I tell you. Okay, so it's definitely wrong. Even for these. Are there even 21 arrays there? I guess there are 21 arrays. Is this off by a digit? Yeah, it's off by a lot, so maybe it's just doing some n square things. It might not, right? So total minus t, print total t, maybe. This would be kind of crazy. But maybe I shouldn't have done this one though. Oh well. Total and t. Oh, definitely both 0 is no good. Let's take out the TLE case. I mean, we know that we previously were right anyway. Okay, so the target, right? I think due to poor scoping, I can actually print out the right, which is actually not great, but okay. So for 1, 0, 1 is not good. What is the prefix array? Let's actually reverse the order as well. Okay, so the prefix array is 0. Okay, so this is definitely wrong. 0 to 8. For 0, 0, 0, we don't update anything. That's actually for 0 is fine, but I guess I don't need this here. The printing is not that helpful. So here we want to say print border total prefix left, maybe. Yeah, okay, fine. So border would be right. Right, so for 0, I mean total is 0 is fine. But then for 1, 3 is smaller so it doesn't get eaten, but then the total is not 3, right? Oh, that's why. I just keep on adding zeros. It was like, how was this right before? How was my TLE solution worked? Oh, I guess I just query it. And it's fine that that number is 0, actually. But here, it is not. 1 is 0 is fine. No. It doesn't get eaten. But how do I add the max? Oh, wait. I forgot that we're doing it in reverse. Okay, that's why. Okay, so 4 is fine. Do I eat exactly the same number? I guess we should. Why not? I guess it doesn't matter, actually. Okay. I forgot that we're going backwards again. So, okay, so for 2, we do not eat, so that's fine. For 1, we also do not eat, that's fine. There's a lot of not eating. People are getting hungry. Okay. But then for 4, we get 3. So 0, 1, 2, 3, 4. So then the 3 we eat on 2, we get 3, and that's true. And then we have 3, 4, 4. Yeah, 3, 4, 4. 2, 2, 4, 2, 2, 4, and then 3. Okay, that's good. And now we have 6, and 6 wants to eat everything, right? 16, right? So then, do I not forget? Did I forget K? What is query mid total? Left should be. I mean, this is just doing left is equal to 0, but we only have this, so we binary search on. I guess any number. So what does this return? I guess we can print here. Okay, so then now for 4 we have, what is that, 2, target is 2, we have 4, is that right? So 6, it eats all the numbers. But this part is not right. It has to be multiplied by something. Man, I am just not doing it. Okay, so what is it multiplying? It should be by the previous number, right? Because, okay, so you have 6. Is that right? Okay, so you have the thing. I don't know why I've visualized this as a square, but that's not quite right, right? If it eats all the previous number, what does that mean? Right, so we have 16 as a cost, which I think is right. The previous is going to be 0, okay. So then if it doesn't, then now you have this width. How do you do this with? You have this width, but you have the height. I feel like this is also where you need the sum of things. But I'm trying to do it without a segment tree, like obviously, because otherwise we already had it, right? Because otherwise, like this, we can probably remove once we get it correctly. But it's just a sum of all these things. But like it's just math on this update, I think. But so it gets eaten. That's fine. Then how? How? Tell me how. I think we have to. Does the binary search require us to do it with a prefix sum like that? With the things we're eating? I mean, we can, but it's just very hard. What am I doing? What am I thinking? Okay, so we have a part. Okay, so the prefix sum part works, maybe, but then now, also well, total is 16, and you minus the things in between. Wait, what is this total? Oh, this is total times t. Okay, so that's the prefix, right? So this comes to 0 because it is the same one, which is technically true. So then it's just this part, and maybe that is the problem that I had again with the thing. And then now I have to figure it out. Is it just another prefix sum, and I'm just like being dumb? I don't know. If I don't know what I wrote, I mean, I wrote this to get the width, but I don't know the height. How do I not know the height? T minus T is just the prefix, and then now the cost. I mean, it would be another prefix sum thing. It's just that it's so annoying to write, and I'm just so unsure whether that works. And whether we only need it for things we're eating. Yeah, maybe that's fine actually. For things we've eaten. I don't know, because that's actually really annoying. I mean, we can do a couple of layers of these things, but it's still just very sketch. Sorry, friends. This is a real struggle. Maybe this isn't right. Or I don't know how to abstract out the. I don't know how to optimize out the query, even with thing. I mean, obviously, if we just do another segment tree, then it's not great. I don't know why segment trees, but it's not great that. I mean, in a way, I am lucky that the segment tree solution doesn't work because even more people would have gotten it. But it's still a little bit unsatisfying to. If this is the case, maybe I'll cheat a little bit now. Let's see. I mean, I got it functionally correct. So okay, so there's a binary search on each one. There's this thing, which I guess what we were doing, kind of. And it's just maths. I mean, this is actually literally kind of what we're doing, right? Unintentionally. But yeah, and then binary search, and then this part is the tough part. Maybe not. This is just an index. I mean, this is kind of what we're doing, but I think this formula is something that I don't understand, maybe. And as a result, I don't know. Like, this is a very convoluted formula, maybe, but with a streak. So this is the last index minus I. So this is a stack. I mean, it's kind of what we're doing actually. So I think we're functionally the similar idea, but I just I mean, clearly I'm trying to put it in more things, but accumulation. I think this part is also. I mean, it goes with this. Okay, so this is the width. This is the. Okay, so this is prefix sum. This is the delta. Okay, so I mean that's kind of what we were gonna figure out with this thing. I'm just kind of lazy with it here. So yeah, and then when we binary search, okay, right? Binary search, we have this thing is what basically what we're doing. Yeah, this is what we're doing here. This is just a number. Oh wait, no, that's basically what we had. So that's a number. That is, so this is the height, this is the width. And this is just a prefix sum. I don't know that I understand that part. So this is the core of the numbers. Okay, let's see. So this is the width, this is the height. But why does this work? Because we had this idea before, right? So we're only yielding numbers we care about. I mean, so this is just this times oh, there's a t, but I mean, if there's an x, that's what we had it before at some point. So there's this. minus the prefix sum from and it's a little bit weird because their index are backwards, but the prefix sum of all the numbers. But why? I guess that just gets subtracted out from the accumulator. Maybe that's why. Like from this part, it like we had this idea very early on. So okay, let's try it. And technically, this is poor scoping, by the way. Do not do at home. I'm just trying to see whether this would work. Index of, well, yeah, I mean, I don't know. Right is crazy. Do I use right? Oh no, because we use right here, so actually that's the wrong scope. This right is a different right. Then, actually no, this should be the same right. That's this one. This is actually terrible scoping, but Alright, let's just border. Let's just at least make sure. We may still be, but you know. How though? It should not. That's weird. This should never be false. Right? This part? No, let's just. Maybe the target part is weird. No? Is the target part weird? Tuple and tuple. Wait, what? Is right? Okay. There's prefixes some weird stuff. Am I being weird? Maybe I am. I'm just having trouble today. Huh? Oh, I have two prefix things. I am silly. Okay, that's why it was outbounds as well. Okay, I mean that should not have ran, so that's fine. Is this? It's border. Border +1. Yeah. I mean, I thought about this idea before, so I don't know why. Okay, this may still time out, but we won't check for correctness because we didn't take out this yeah, we didn't take out this segment. Though maybe that's fine, honestly. Well, we'll see if it's fast enough. We didn't take out the segment tree, obviously, but so okay, that's actually wrong. Yeah, there's something weird about this formula mostly because I just copied it, right? So okay, so this is the prefix sum part. This is the height minus the thing, which is fine, but okay, so 6. Clearly, we only have 3 + 1. Why does it think I have 5? Only way it had 5 is 2 and 17 maybe? I don't know. 0, 0. Yeah, I don't think, yeah, this is not right at all. 0, 1, and then 2, 2. Oh, I'm going backwards again. I mean, that's actually fine, but they're now searching for 2. Okay, the reason why this is because this is 0. So when you search for when you binary search for okay, let's think about it anyway. Two total. The prefix total is 16. Prefix. Okay, so it thinks that see what 115 is. Oh no, that's right. So then, because I forgot that we're always going backwards, but okay. 2, 2 is 15. Okay, so that did the math backwards in some way. Because basically here, it thinks that it could get to, so 0 will return 15, which is definitely too big, right? Oh, but then the 0 to 1 has a prefix, which is true. So then now, if it's 0, then you have 0, 1, you have 17, okay. Yeah, okay, let's just put it. Okay, well, that's definitely not right. This is the right, oh yeah, I swapped them. Sometimes all it takes is one print statement and it's easy to see why you're wrong instead of kind of working it out. Okay, now it's really wrong though, but that's fine maybe. Yeah, because okay, 2, 17 should have 1. Yep, this should have 2 though. Okay, so it binary searches for what does it binary search for? It binary searches for okay, 1 is definitely fine, but so then this math, right? You have to do this math. And then it is 17 is 15 to do this. So this is 0, or should be. So then you have the width. Oh, I don't. Why does this X work? I think it's. That's, I mean, I don't know. I don't know if that's the reason, but it's definitely, it doesn't help. So, okay, let's just add this. I don't know. Nope, still wrong. Yeah, and then now, but at least this, I think this number changed. I don't forget what it was. But okay, so then it's 17. It's the current total, which is true. No, can only be 15, so 17 doesn't make sense. So it goes to 17. Which is the index that it thinks is matching? Okay, that's the right one. For target 1, okay. So then now this is length 1, it's times 17 minus is this right? No, I don't think this is right. Should be just target minus p right. Yeah. Okay, I fixed this one, but now all the other ones are wrong. Well, the other ones were wrong anyway, but okay. Okay, so why? Okay, let's print a little bit less first. One, two. Is this right? It's 4, 4, that's right. So yeah, 1, 1, 2, 3, 4, that's 10, right? And then 12, and then 13. Okay, well, why? Okay, so the 1, what is the constraint? 7? That's only 3, 4, 5, right? So this one definitely should go more than 3. Oh wait, 0, 1, 2, 3, 4. So that's 3. 3, we have 1. What's this? 3, 5, 1 should be 6. So now this should still go all the way. Yeah. Okay, sorry. I'm getting distracted because I'm just so tired. Okay, so 2. So the target is 2. We have to the target is 2. The total is 3, which is 5. No wait, we should do. No, this is the right one. Oh yeah, am I putting the right thing? Okay. And then the target is 2. For 2, we get the sum is total is 10, right? So which is false. We have only these 3. Then now the answer is 10. Why? That doesn't even make sense. Okay, so you have this thing. It tries to find the 2. It finds the 2 here, which is true. And then it does the 3 times, so that's gonna be 9 minus 6, right? This is awkward that it's putting out negative numbers. That should definitely not happen. But okay, P right. Right, let's print this out anyway. Am I missing something? Oh, this one. Okay. What? Oh, right. Sorry friends, my body is getting a little tired as well, but okay. So -1 is definitely not right. 9 is fine, this is not right. We have the n prefix from target plus 1. Oh, is it no, target is right. P right should be the section on the right. P right should be the biggest number. No, this is wrong. I mean, yeah, I think that's well. I mean, I think we fixed this, but or changed it anyway. Clearly not fixing it. Oh wait, huh? Did I? Maybe I had another thing that I kind of messed up. I thought I had maybe I had the wrong index. Maybe I had right instead of thing. All right, let's try again. Again, we're looking for a TLE because we didn't get rid of the segment tree, but we just want to check for correctness. Once we got this, it's fine. Also, it's kind of like these kind of ideas is how you would think about, you know, in a way, this is TDD, right? So we're building one step at a time and refactoring one step at a time. Very painfully, I might add, but yeah, I don't know why this works though, because we thought about this like way early on in the problem, like even back in during the contest days, but I guess it works because of the way that you compress, so everything inside is the thing of this, I guess geometrically, but that is so hard. I don't know. Okay, we can now figure out how to, not do this update, right? Maybe. Let's see. And we can kind of lie, right? And what I mean by that is that, okay, this takes, let's take a long, how long? We did like a few more test cases, so that's good. So this takes 2 seconds. We can maybe, just see what the possible thing could have been by just kind of putting in crappy numbers and then kind of just see, okay. So you can see that this gives us at least a 3 times, obviously the answers are wrong because we're not querying the right thing, but 3 times improvement on just this one case. So we definitely need to do something like that, right? And then now we just have to think, okay, what if we just got rid of one of them? Well, I guess then it's just silly because the other one doesn't do anything, right? Like this doesn't do anything. But okay, so now we're trying to get rid of the segment tree finally, right? Okay, so the idea would be to, as I said, prefix sum. So here, here, how would I do this, right? So this part is, okay, well, current is kind of simple, maybe. Well, okay, so we only need to update for using it for here, right? So we only n log n actually, but it's still too slow actually, right? I mean, apparently. So then now we want to say, yeah. So, okay. We want to say sum is equal to maybe current is equal to this, right? So then current we added by L index or R index minus this plus 1 for length times x minus px, right? For the things we popped. And then now when we finish popping, let's comment. I was going to delete it, but then current, well, current is just equal to current. That's actually terrible. But okay, fine. Then now it would be the last index plus the thing on top, right? So plus prefix the last one's 4th element, right? Wrong element. And of course that's only if it has a prefix. Okay, I mean it's wrong, but it's fast. That could be something. I think that should be right though, right? Oh, this is this plus prefix of negative the current t, right? So this is this should be, what was the t, what's prefix? Left do. Oh man, I thought that would work actually, honestly. So that's the maybe I don't need the prefix as a result, because that's factored into the t, maybe. Nope. Okay, I just have to work it out. I mean, I think this is fine, but we have to work it out. Okay, so this part is fine, but what do we do with the previous t? No, I mean, this is the sum of all the other numbers, right? So that goes up to this range, so I think this should be right. And then here, it's just of all the numbers that we haven't cared about yet, right? So I don't know why this is wrong, actually. But it is fast. X plus 1. This is definitely the difference. And then, okay, so maybe we can, and we didn't get rid of the segment tree yet. So, okay, let's use it again. So then we can now assert st dot, was it get range, is it? That way remove it? Let me try. I think it was get range, but yeah. Query range. Okay, well, query range from L index to R index is equal to this thing, I suppose. Maybe if that's wrong, then that means that this T is weird and wrong, right? So that's why. But there are some other moving parts. Oh, just because I'm popping the wrong thing. Is that it, Larry? Are you a Dumbo? I mean, it still might be, but that is silly. I made the same mistake here, so okay. Okay, so it's still wrong, so that's not great. Okay, so let's just say before we do it. Okay, so that's not good. Why is that? So current leftmost, rightmost. Oh, because this is the prefix sum. Is that? Yeah, that's fine. That's what we want, right? Yeah, that's what we want. I think that's what we want. Okay, so then here. So okay, so this is 0 if okay. So what is the condition? Initial condition, right? So stack print prefix. Okay, let's see. Where does it go wrong? Actually, it goes wrong pretty far in. Which is actually surprising. Actually, in the exact case. Okay, so and then second one, and then here on line 103. Okay, then now maybe an assert should be here. st query range of, because that's what we were setting, right? We were setting, okay, current is equal to from leftmost to right, and this works maybe. Yeah, I mean I'll put limit exceeded because we're putting too much, but so this works, but that's a crazy amount. Actually, don't know how that would be. that doesn't even make sense. Maybe it makes sense. I don't know. But okay, so that means that print current this, right? And apparently that's wrong or does not match. Maybe the output's limited anyway. So okay, so this, but then this becomes 0. The query becomes 0. Oh, because it's not the prefix then, is it? It is just a chunk. Okay, so query range is not. Okay, so this is I mixed up two things. So this is not prefix. So what was my wrong answer? Okay, so this is the thing. But I go from 0 to right. Oh, okay, yeah, I'm just being dumb actually. So does this give me the right answer? No, so okay, so that's why I'm being dumb. Actually, this is not leftmost. This is from 0. So we want this, right? Okay, so this is the right answer. I'm confusing myself a little bit, right? So then now we want to assert current is equal to st.query range 0, right? Okay, so that already is wrong, which is fine. That's good actually. Maybe we should retain the print. Okay, so 3 numbers in. Why is that wrong? Oh, I guess we need the last 3 numbers really. Okay, fine. Let's just print number subray. Okay, so, right. So you have some big number, smaller number, and I forget which way it goes. So this does not yeet. So then this one yeets this one. So I guess this is the delta, right? So then why is current so big? Did I add the wrong number? That would be funny. 0, 1, 2. No, that should be right. Let's see. What happens if we don't do this? I mean, it'll just be wrong, maybe. Or should be. Right? Yeah, it should be wrong. Or more plainly wrong. Okay. So then why is this? Okay, so this is definitely right. Right, so this is right, so this is not right. So that means that this is a little bit funky because, okay, so let's print out prefix, right? So okay, so we have this and oh, we have 3 numbers in. This is actually the 4th number. Maybe I missed the thing on the print statement. Okay, so then this consumes this number, right? I guess we can actually just print out the before after. Current is equal to 0. No, the states make sense. Okay, just want to double check the states. So okay, so you have this, it eats this, or it ate this, which should. And then now, however, five, 4, but then the query is right, then current is wrong. Why is current wrong? Do I need that? Maybe that's it. Nope. Because then this should be 5 something, right? 5 prefix, 5 something. Plus 131 should be. So why did I get this? Oh, because I consumed this as a prefix sum. Okay, so we consumed this, but then we added this twice. Because this is not the number, this is the prefix sum. So then we need the prefix sum by calculating the difference between the last 2 elements. Because this is, okay, I see. So then now to get the value of this, you need to get the y. Okay, fine. So this is not t, it is actually, yeah, if length of, this is so hard to get right. Oh, but this is an optimization that I feel like it's a little bit silly, honestly. I mean, it's a little bit faster, but it's the same performance, right? So I don't know. But I'm just doing it for my sake, honestly. But okay. Okay. So this is plus t, but in a prefix some kind of way. So then we subtract it from, and this is prefix. Prefix of -1, 2, right? Get the prefix sum. if it runs out of time or output limit exceeded, that means that we haven't hit the assertion, so that's good. Still output limit. I have a lot of print statements, I think. Okay. That's good. Okay. Take out the assertion, right? That should already cut out on time, and I think this update range. Yeah, but this is faster. I don't know if it's fast enough. And its function is going to be different from, or same as, you know, people's solution. But yeah, okay. Yeah. I mean, I don't know. The annoying thing is that this is the same complexity, right? So, sorry, I had to catch a breath. I mean, you know, it still takes 7 seconds. So yeah, it's a little bit wonky. And of course, here we can actually just get rid of the segment tree now, I think. And let's clean up the code real quick. Oh, well, maybe even faster if we just remove this. But that should also point out the statements. But also, this is why we need a sentinel for prefix, which I did not do. So actually, maybe we could have done what is it? I don't know. It shouldn't matter. Just -1, -1, 0, 0, right? So then now this will always be true. Is the good thing. Is why I said it that way. If not, then I chose the wrong sentinel value. X is greater than that's on. Oh no, that's on stack, not prefix. But yeah. Okay, let's see how much faster that is. Oh, it's right here. Not that. If anything, slower. So that's actually surprising. Maybe that's just fluctuation though. Okay. Can I do a little bit better? I don't know. Honestly. No, I mean, I feel like the obvious stuff should be good, but I don't know. This should not need this optimization. Actually, apparently someone did do it with. Maybe I'm wrong on this one. All right, let's think about it for a second. Because right now we still do 2 binary searches, right? But can we do it in 1 binary search? Someone seems to be able to do it, and they let me know. So in my Discord, now that I'm peeking a little bit, honestly. Okay, so. I mean, this is probably have to be this part, right? I mean, this is still n log square n. How would I think about this? Can I think about this? this is just to get the border, right? Can I incorporate them together, right? So it goes for each index. I don't know, maybe I don't understand the there is a log n or n log n solution apparently, but I don't know that I understand it. Oh, I see. I understand it. Because basically here we're still binary searching on the border, on the index, but we can actually binary search on this itself and then just tick whatever is necessary on maybe even a second binary search, but then that binary search would be within one chunk, so you only do okay, let's try that. I mean, this is a very long video, but I think this is kind of okay, fine, right? Because then now we can do what left is equal to 0, oops, right is equal to length of prefix, right? So then now left to do, right? I don't know why I wrote it like this, but it's fine. Then now we want to get okay, so total is going to be whatever, so then total minus prefix of mid, right? Yeah, so if total minus the prefix of mid of what's it, -2 is the prefix prefix sum. So if this number is greater than or equal to k, or if it's less than or equal to k, then we're good, and we want to try a bigger number, right? So then right is equal to mid, oops, else left, oops, left is equal to mid plus 1. We have to try a smaller boundary, or is, wait, is that the prefix is the distance, so then a smaller number is, yeah, okay, I think this is right. And then now we can do this thing, which is that, okay, maybe we can even do this. So index, well, left is equal to index, right? And then now we binary search within this chunk, right? So then current total is going to be this thing, and then while, okay, oh sorry, index is equal to left, right? So index is equal to left, and then now we try it again, which is that left now is equal from p left, right is equal to p right, so we do a second binary search. I mean, maybe there's a smarter way to do it. I think you could actually solve for the formula, but it's fine. I'm yeah, for now, right? So then now, if current total, you could even probably solve this in a smarter way, but I'm just gonna write it out, right? This thing. If this number is greater than equal to k, then that means that this number is good and we want to try a bigger range. So that means that right is equal to mid, else left is equal to mid plus 1, and then at the end left is going to be thing. So then now current total we added by the left, right? So let's just say f is equal to left for found, and then f, right? And then what is this? I don't know what get does anymore. Oh, get is the count. Oh, yeah, I guess we can assert current total is less than k. I think it doesn't matter. Actually, this is just f. Actually, this is also just left, which is kind of terrible, but okay. Okay, that's not great. Why is that? What if we just don't do it? Or we just ignore it? Okay, still wrong. Target. Where do we have target? Oh well. How does this not mess up? This is mid, right? And I don't mean it as the way the kids say it. Maybe that's why it was wrong, but okay. So then now let's just say we're at this, and then we're gonna insert it real quick. Why is that wrong? Okay. Print left, right. Okay. Current total is good. Okay, that's fine. Okay. Because we assert that so right is equal to mid, so that means that we want to try a bigger number or smaller number. I don't know why this doesn't work, but I mean the idea should be okay. I forget what I'm doing anymore. Why is it assertion error? Left right is -1, -1. Oh, because it's doing it on the sentinel. Okay, fine. But what? Why would it be? We search for prefix. So total is what is? Do we even use the border anymore? I guess we don't, right? Because it's implicit. Okay, let's just say get and the prefix total. Make it a little bit less confusing, right? Still wrong, of course. We have -1, -1, which is, I mean, this index is 0, but why is it 0? I mean, this thing is 0. Let's say we don't search for 0, but that still shouldn't make sense, though. Total minus this is, if total minus this, maybe this, I think it's a smell more than anything. So okay, so this is, if this is smaller than k, then we could try a bigger number. I guess this just means that if left is 0, that means that we try all the biggest numbers, and then here this would just trivially do nothing. P right minus f. F is not right. Left is the index inside. No, but that's fine. It's just that this is -1, right? It's because it's -1 that this is, no, but -1 minus -1 should be, oh, so it's assumed that, but then x is 0, but then it doesn't have, oh, okay, so this is minusing a huge number because of the way that we do f is -1. Best laid plans on your sentinel values, I think. But it's a good thing that, you know, I think this works, honestly, but let's see. Border is not defined. I guess I did need the border to I lied then, to get the size. But, well, am I just putting everything? The ends is right. So, yeah, where's my print? Okay, let's get rid of the print. Okay, let's give it a submit. This is a very hard problem. I take it back about the segment tree because I think that was just a smell. But yeah. let me give credit. So on my Discord, I think Joseph and Ace kind of talked about it. I didn't look at Joseph's solution, but actually Joseph has like a crazy solution that is maybe linear, but unclear. I see what he's doing, but it's yeah. I'm trying to look at Joseph's solution. So this person Ace on my Discord. I mean, I just had to know. I think from his solution, I don't know how much I copied it or whatever. It's just that knowing that n log n exists, and I didn't, because I was optimizing an n log square n, right? And I think that's why. Okay, maybe that's fine, right? N log square n versus n log n. I don't know, and also it's kind of weird, right? Because I don't know if that's for science. Let's see if this would work in, say, Java, right? So let's ask ChatGPT, and this is kind of why Leetcode is a little bit silly sometimes. Can convert this to Java, and then we'll see whether this works. The old segment tree solution, because I don't know, but n log n solution is beautiful. Just knowing it, I think, allowed me to kind of, because I wasn't thinking about optimizing it. I mean, this makes sense. And then Joseph has a maybe linear solution, unless I'm reading it wrong. But the idea is something that I was trying to do with this prefix array. But I don't know. Or the difference away is required, but I don't know how to do it that way. Or at least without doing it like really crazily, right? Time wise. Like, how do you get the query? I mean, I guess I see it actually. Because it's just a prefix. Yeah, I mean, I'll go over it in the. I'm not gonna implement this part because it's just at this point it is a very long video. But I'll just put it here and then I'll go over why that works in the explanation. Yeah, I mean, honestly, it's fine. It was a fine contest. A lot of people got it, huh? Q4. I think I wish I did Q3. What the sports table. I'm curious about this because I was trying to do something like this, right, with the RMQ. Did they do it with regular RMQ? Yeah, I mean they did with the regular RMQ, so I'm trying to figure out how to make this work. Well, some of it is that I was doing it backwards. Is it as simple as that? Oh yeah, this is n log. I mean, I've and maybe it doesn't work in Python. I don't know. I am gonna try to figure it. I was gonna say that if I had a faster Q3, you know, this would have been like, well, okay, this crown is actually a crown, but like I feel like this would have been very reachable and would have been okay. But I think I am curious whether like my first submission, this one, the RMQ one. Yeah, I think with this submission, I do wonder if I had one that isn't RMQ'd. Like, would this work if this was reversed? Like, is that what I was missing? No, because they did the binary search without this. Actually, I don't get. Yeah, never mind. I don't think I understand how that works. With the, let me see if I can find it again. Well, people are really into writing, you know, ChatGPT Leetcode. Okay. Oh, there is a sliding window one. I was trying to do something like this. I don't. Oh, well, I mean, I didn't reverse it. So I think that. No, this wasn't even in reverse. You have the current max. You add the delta. Okay, so this part we got. So then now we have a for loop or while loop, really. Why don't they just use stuff right? This is an n square loop, right? So I guess this should be changed. That would be funny if it passes. Maybe it's just like a Golang thing. Like maybe it's just fast enough in Go. But but yeah, this. I mean, unless there's some amortization, but. I mean, I don't know. I guess that I was wondering because I was doing the same thing, but I wasn't trying to do it like the n square way. But like what is this? Maybe I just sucked at math. I don't know. Like I feel like, and I don't know how much of it is because I didn't think about it backwards because I was thinking about similar things, but so this is, you know, this is just regular sliding window, right? Except for that went backwards. I didn't think backwards. I think that was my struggle. So then how do you do the slide? How do you get the L? I mean, I'm taking an L. Oh no, L is the loop. And then, okay, but how do you get the right? Okay, so all right, oh, huh. Can I do it that way? Was I just being dumb? I mean, maybe. I mean, I think some of the struggle is because I didn't. Some of the struggle is because I didn't think about it backwards. I assumed that it would be symmetric. I at some point I did know that it was not symmetric, but then I just didn't. And maybe this is what this solution is kind of like. But let's see. Let's do it the Larry way. Maybe I will do it my way. Because I thought they would be symmetric, but this is not a symmetric problem, and as a result, even though at some point I knew it wasn't symmetric, but I didn't analyze it enough. Okay, so now let's go backwards, right? I thought it would be symmetric, huh? But yeah, okay, so then now let's go backwards. We have, let's just say, yeah, Okay, so how would I do it, right? So for x in nums, right? Let's just do it as dumb as possible and then we'll figure it out. So cost is equal to 0. Cost is equal to 0, and then yeah, and then we have a current max. I guess we have to enumerate. Maybe that's a little bit, but I think we do need to keep track of the index the way that I think about it. Okay, so then if x is greater than current max, then now current max is equal to x, right? And maybe we have a q. And here we append current max, or maybe index current max, right? And then maybe the current cost as a prefix cost, maybe. I don't know. I don't know how I feel about this one, but okay. So well, let's just say if it's equal to, right? So then else delta is equal to current max minus x. So then cost we added by delta, right? I don't get it. How does that work? Right? So then now okay, I need a case to walk me through. Okay, let's just say about this, right? Okay, so you have 4, and then you're fine. Right, the cost doesn't change. Now you have 2. You have 2, right? I have to think about. I think in some of the reason is because I analyzed this so much from the other direction that I think I'm stuck on things that are no longer true in this direction, but confusing myself, right? So then here we have right? So we see a smaller number. That's okay, right? Yeah. Then now. Yeah, whoops. If this is greater than max, then right? Otherwise, if this is smaller than max, this isn't true. If it's greater than max, then the cost from a prefix perspective is going to be equal to am I doing this one? I'm just so many hours in that I'm a little bit confused. Okay, so then now I'm forgetting about whether it's increasing or decreasing and all these things. That's why I'm going. So we want to make it increasing in this way, so then it'll be decreasing in the other way. So then that means that if this is a 2, we're okay. But if we see a bigger number, then we have to do a cost thing, right? So then that means that from 3 to 1 to 3, then there's a cost. So exit. So there's this thing, and then you have this thing, right? So because this is well, then now this consumes to the left, right? That's okay, so it consumes to the left. Okay, so then now we have this, right? Okay, so then, okay, so here we okay, let's see. Q is greater than 0, and maybe we just consume to the left. Whatever, right? Doesn't matter. It's just a bucket. Is less than X, then we want to consume it. Right, so then Q dot pop right, or just pop. And then cost we added by the index, their index. So then the previous X, previous index is equal to this. So then now it's just the previous index minus the index, not including this number, so that's fine. Okay, let's say we consume, and this will always be increasing number, right? So that consume this, so this we subtract it by and now what happens to the 2? The 2, it's not p index minus index, right? So this is just the delta of these two, right? So one would have the value of all the numbers it consumed, so then yeah, okay, so it's p index minus, let's maybe, didn't I already write this though? Like, yeah, I mean I did it with a stack. Maybe I don't need to do it with stack. Maybe this is a, you know, maybe this is not a stack. Yeah, I mean, I think I could just reuse this though. So, yeah, let's see, what did I do? Except for that, now this is a queue. Right? Yeah, so then now you have, let's just say cost is equal to 0. Right, so then now you consume it. You consume it, px left index and then the total, right? Okay, so maybe this is really the same, but yeah, so then that's fine. We subtract it from the previous. Do we want this to be a prefix? I don't think this is a prefix stack anymore, so I think this is fine. It's just all the stuff that it ate, right? Okay, so then now, and this is actually a right? So then now left is equal to 0, right? As a regular sliding window. The right we actually don't use it yet, but yeah. So I think it's just like right minus left plus 1, the classic count. But then now we have to do the cost. How do we get the cost? We just keep the cost of the entire queue, right? So then here, if we pop, then cost we subtracted by our index minus, we subtracted by t, but then we added by this thing, right? Which of course, then now you can take out the t. So then this is the difference to the cost after you consume it. Okay, that's fine. And then now, while cost is greater than k, then now we want to consume left. So consume from left, right? So q dot so while length so if q is greater than 0, well, we have to assert this, I think, and so I guess actually here this will already be true because we will add in x leftmost right t or cost, right? Yeah, so cost is orders costed 8 up. Okay, is it though, Larry? No, cost is the thing inside the window. T is just the thing inside. Why do we need T? Oh, so that next num. I don't know that we need T. Actually, maybe I'm lying. Because by definition, yeah, what is current? Maybe we don't even need current max. Maybe I do though, I don't know. But I guess current is the cost is the things inside the queue. You do this. We yeah, this is the difference, and then we put x in, right? Okay, and then now we want to remove left. We want to remove 1 from left. So yeah, if q of the first item in queue, the right index is greater than or is less than left, because when it consume, that's good. Otherwise, then now, if it's greater than left, then we pop left. Otherwise, then here, cost we just subtracted by x. Wait, what is the, maybe that's the part that I'm confused about. Otherwise, then we consume it by how? Okay, let's say we have a 6, we have a 3, we consume. Let's say it's too much cost, then now we move to 4, right? You don't subtract the x. Okay, I mean, moving this 4 is easy because it doesn't do anything. I guess we're moving this 4 either, but this is the 4 minus num sub x or num sub left, and then left increment. Is that it? I mean, I'm doing way slowly, obviously, but that's fine. It might not even be right, so, you know, if it's not right, then it cannot be. Okay. Why would this one out? If the right index is greater than left, nope. If left is greater than the right index, then you pop. Alright, let's give it a submit. Okay, left goes out of bounds. Why? Does it go to 0? So if it's decreasing, then it should just be 1, right? But if it's one element, left, right, 2, 2, cost should be 0, but apparently not. Okay, why? Am I doing the x wrong? X is wrong. X is not x, it's q of 0, Larry. Well, x should be here, but I think I'm overusing x, so let's just say y. I am being dumb. Okay, now SSY. Otherwise, oh. No, this, what am I doing? But it is very late. I've been like 3 hours on this one problem, so maybe that's fair. It should never be 0 though, or like it should never have no elements, because by definition, if the rightmost element is outbound, yeah, okay, why? Yeah, okay, but why? Oh, no, that's right. Okay, so you have 14, so you go 4, 9, and then 9 consumes the 4. You have 0, 1, yep, and then 14, okay. Then what's the cost? Why don't I print the cost? Okay, so then the here, 9. So the 4 minus 9, that's not quite right. It's 4 minus the current number, right? I think that's the part that I'm still like confused about. I think I had similar ideas before. Why is this wrong? Well, like how do I attribute this to? Well, no, it attributes to 14. So 4 minus 14 is 10. But it just subtracts 5. So, okay, so this gets rid of it real quick. So you have 9. But the cost is too high. The cost is too damn high. Is this wrong? Okay, so then now we can see. So okay, so 0 to 0 is 4. Okay, this is right. This is not right. This should be 15. Or the cost should be 15. No, this shouldn't be from 0 to. No, maybe it should, but the cost is wrong, right? Index minus less index plus 1 plus the previous cost, right? No, but the previous cost is already in cost. That's why. So cost is 5. So now you have 5 plus 2 numbers, right? I don't. Okay, this is fine. Consume, the cost is 10. It assumes the 9, but which is fine. But then the width is wrong. X minus px. Five times 2. Oh, 14. No, but 5 times 2 is 9. Oh, we need it to be plus the previous thing, right? Why did I get rid of that one? Yeah, I don't know. Maybe I'm just confused. Oh, because no, but it should be in cost. That's why, right? Because yeah. So 5 times 2. Okay, so consume 14, 5 to 10, 5 to 10, but cost was already 0. Oh, cost is 0 because you remove the 9, removed the 4 because it's too big. Oh, then I have to, I guess the left is wrong here, that's why. So then now, okay, so then, and then when it gets consumed, it's different. I see. So then now, assert that q sub 0 of 0 is equal to left, and q sub 0, 0, right? After this, anyway. Oh, we popped. Why? Where is this wrong? 0, 5. Okay, well, I mean 6. Oh, no, I'm looking at the wrong element. Left is... Okay, I mean, we used tuple. Where's my tuple? I thought I used the list today, because I thought I need to do something like this. Deck out of range. How? Because of this thing. Left, right, Q. Then the math is wrong for cost then, right? Okay, so that means that we subtract 1, right? We increment by 1. The cost, that should be right, right? Oh, this is wrong. It's not. How do I keep on using the wrong index? I just confuse myself a lot. Right. Huh? I just got rid of print statements. Oh, did I do that? Did I print out the... I comment out the wrong thing. All right, let's give it a quick submit. Yeah, I mean, I think this is way easier. I think I overcomplicated this. I think it's just fundamentally I was looking at it because I thought it was symmetric, but okay. I mean, we solved Q4 in many ways. I think I just didn't find. I talk a lot about the invariant, and that's basically what happened. Where I just did not find the invariant, and I was just confused about Q4. But it was a struggle, was clearly. But ultimately, I think I got what. I mean, it's hard to say honestly because I think my biggest mistake was not thinking about it backwards because I thought it was symmetric for some reason. And usually it is, or like very often these things are, but this one is not. And as a result of not looking at it backwards, I didn't analyze a lot of the things that I wanted to do. And even when by the time I did think about it backwards, like in the contest, after the contest, I had too many preconceived notions of what's going on that I was just going a little bit nuts. Yeah, that I was just going a little bit like because that's the thing. It's really hard to reset during even after a contest, after a problem. That's why sometimes it's worth it to kind of go do something else and come back. But as you can see, I'm stubborn. Spending 3 hours on this problem, really 3.5 hours. But yeah, but as a result, and what I mean by that is that there are properties that I found in one direction does not hold in the other direction, but in my mind it's very hard to confuse which one is, or it's very easy to confuse which one is which, and wasn't able to kind of separate them out. And then I didn't try certain things because I thought that those observations were still true in the other one, right? So I think that's the idea, or that's why I struggled too much on this one. But you know, I think I learned some stuff. But I think I think the tricky part is I don't know if, like, if you told me that this solution exists, like, and you kind of saw it, I was able to work it out. So I don't think there's anything crazy about it. But today I missed that one insight about looking at it backwards, and as a result, like even when I was thinking about it, I wasn't able to think about it because I analyzed too much on the other direction. It's tough to reset. But yeah. Anyway, this is all. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy to your mental health. I'll see y'all later and take care. Bye bye.